Red Bull, Monster, and Celsius are the high-octane drinks fueling millions every day. But behind every can is a fast-paced, precision-driven process that mixes science and sheer energy into one powerful package. Today we're going inside the factories to see exactly how these energy drinks are created from the first ingredient to the finished can. Red Bull starts with its formula, a carefully guarded blend of ingredients that deliver its characteristic taste, texture, and functional effects. At the heart of the recipe is water, which serves as the main ingredient by volume. This water is not simply pumped from a municipal source and used directly. It undergoes multiple purification stages to ensure it is free of any dissolved solids, minerals, or microorganisms that might alter the taste or stability of the drink. The purification typically begins with coarse filtration to remove particulate matter, followed by activated carbon filtration to strip out organic compounds and chlorine, then reverse osmosis to achieve a very low mineral content. The final step often involves ultraviolet light treatment or ozonation to sterilize the water before it enters the production tanks. Once the water is ready, the remaining ingredients are prepared. These include sucrose and glucose for sweetness and energy, citric acid for acidity and flavor balance, taurine as a functional amino acid, caffeine as the stimulant, and B-group vitamins like niacinamide pantothenic acid, vitamin B6, and vitamin B12. Each of these arrives at the factory in bulk form. Sugars as fine crystals, taurine and caffeine as purified powders, vitamins as either powders or highly concentrated solutions. All are stored under controlled conditions and tested in an in-house quality lab for purity and potency. The creation of the beverage begins with the preparation of a concentrated syrup. In large stainless steel blending vessels, precise amounts of sugar are dissolved in purified water under gentle heat, usually between 50 and 60 degrees Celsius, to speed dissolution without caramelizing the sugar. The glucose syrup, if used in liquid form, is pumped directly into the blending vessel through sanitary pipelines. Once the sugars are fully dissolved, the other functional ingredients, taurine, caffeine, and vitamins, are added in carefully measured doses. This mixing process is critical. Operators rely on automated ingredient dosing systems connected to load cells and flow meters to ensure exact quantities, as even a small deviation could alter flavor or regulatory compliance. Citric acid is then introduced to adjust the pH, giving Red Bull its slightly tart backbone and enhancing stability. Flavors, which are part of a proprietary blend, are also incorporated at this stage. These may include natural and artificial components that together create the drink's distinctive aroma and taste. The mixing tanks are fitted with high-speed agitators to ensure uniform distribution of all ingredients, and the resulting syrup is tested in the lab for Brix, acidity, and flavor profile before moving forward. Once the base syrup is complete, it is diluted with more purified water to bring it to the target concentration for the finished beverage. This final liquid mixture, now containing all flavor and functional components, is chilled to prepare it for carbonation. Carbonation is one of the defining aspects of Red Bull's sensory experience, and it is performed with great precision. The chilled beverage passes through a carbonator where it is brought into contact with carbon dioxide under high pressure. The CO2 dissolves into the liquid with the level carefully controlled. Too little carbonation would make the drink taste flat, while too much could affect mouthfeel or cause excessive foaming during filling. The carbonated beverage is then immediately directed to the filling lines. Red Bull is packaged almost exclusively in aluminum cans, chosen for their lightweight nature, excellent barrier properties against light and oxygen, and recyclability. These cans arrive at the factory in massive stacks of unprinted or pre-printed containers, each one spotless and free from dents or imperfections. Before filling, they undergo a thorough rinse with deionized water or ionized air to remove any dust or debris. The rinsed cans move down the line on high-speed conveyors into the filling carousels. The filling process operates at incredible speed, often hundreds of cans per minute, and is performed in a pressurized environment to maintain carbonation. Each can is filled from the bottom up to minimize turbulence and foaming, then immediately sealed with an aluminum end by a seaming machine. This seam is a precision crimping of the lid to the can body, creating an airtight and watertight seal. Once sealed, each can is inverted briefly to ensure the lid is fully sanitized by contact with the beverage inside, then returned upright. Immediately after sealing, cans pass through automated inspection systems. These use a combination of cameras, sensors, and weight checks to identify any underfilled, overfilled, or defective cans. Any can that fails inspection is automatically rejected and diverted from the main conveyor. Approved cans move on to pasteurization or cold sterilization, depending on the plant's process design. Pasteurization involves heating the cans to a specific temperature for a set time to ensure microbial stability, while cold sterilization uses aseptic filling combined with sterilized containers to achieve the same result without heat. Once the cans are confirmed safe and stable, they head to the secondary packaging area. Here, they are grouped into the familiar 4-packs, 6-packs, or larger cases using cardboard wrap or shrink film. Automated cartoners or shrink wrappers handle this at high speed, often in combination with robotic case packers that load the multi-packs into corrugated shipping cases. The shipping cases are sealed with tape or hot melt glue, coated with batch information for traceability, and then stacked onto pallets by robotic palletizers. The pallets are wrapped in stretch film for stability and transported to a climate-controlled warehouse. Although Red Bull is shelf-stable at room temperature, storage away from excessive heat or direct sunlight helps maintain carbonation and flavor over time. From the warehouse, pallets are loaded onto trucks bound for distribution centers and retailers. Given Red Bull's global reach, many of these pallets also enter intermodal shipping containers for transport by rail or sea to other countries. Throughout production, the emphasis on quality and consistency is relentless. Every batch of syrup and finished beverage undergoes analytical testing to confirm caffeine content, vitamin levels, acidity, and carbonation. Sensory panels taste samples to ensure the flavor matches the established profile. On top of that, microbiological testing verifies that no harmful organisms are present, and shelf life trials confirm that the product will remain stable through its intended storage period. The machinery in a Red Bull plant is highly automated, reducing human contact with the product to a minimum. Operators oversee systems via control rooms equipped with touchscreens that display real-time data on mixing temperatures, carbonation levels, filler speeds, and line efficiency. Maintenance crews work behind the scenes to keep pumps, compressors, and conveyors in top condition, as any downtime on a high-speed beverage line can be costly. Sustainability is also a growing focus in Red Bull production. Aluminum cans are already among the most recyclable packaging formats, and many plants source cans with a high percentage of recycled content. Water purification systems are designed to minimize waste, and heat recovery from pasteurization can be used to preheat water for syrup preparation. Efficient compressors and motors reduce energy consumption, and many facilities work to optimize transport logistics to cut fuel use in distribution. What makes the Red Bull process particularly interesting is how tightly controlled and repeatable it must be. The drink's formula is identical worldwide, which means a can produced in Austria should taste exactly the same as one produced in the United States or Asia. Achieving this level of uniformity across multiple plants requires not only identical recipes and ingredients, but also standardized equipment, operating procedures, and quality control protocols. Every plant is essentially a mirror of the others, ensuring that no matter where it's made, Red Bull delivers the same signature flavor, carbonation, and energizing effect. Every can of Monster begins with its ingredients, and the largest component is water. The water used in Monster Energy production is not simply drawn from a tap, it is subjected to a thorough purification process to remove any dissolved solids, organic compounds, or microorganisms that could affect taste, appearance, or stability. The typical sequence starts with coarse filtration to catch sediment, followed by activated carbon filters to strip out chlorine and odors. Reverse osmosis membranes then reduce mineral content to near zero, creating a blank canvas for the flavor formulation. As a final step, ultraviolet light or ozone is used to sterilize the water before it enters the mixing tanks. Next come the sweeteners, functional additives, acids, and flavors that give Monster its distinctive taste and energy-boosting profile. Cane sugar or beet sugar may be used along with glucose or high fructose corn syrup, depending on the variant and market. These sugars arrive in bulk either as crystalline solids or liquid syrup in tanker trucks. Functional ingredients include caffeine for stimulation, taurine as an amino acid additive, and B vitamins like niacin, riboflavin, vitamin B6, and vitamin B12 to support energy metabolism. Some varieties incorporate plant extracts such as ginseng or guarana, which add both flavor and functional appeal. Acids like citric and sometimes malic acid adjust the pH for tanginess and preservation, while natural and artificial flavors create the unique profile for each Monster variety, from the classic green logo flavor to tropical, coffee-based, and sugar-free blends. The first main step in production is the preparation of the concentrate or syrup. In large stainless steel mixing vessels, sugar is dissolved into heated purified water under gentle agitation. If liquid sweeteners are used, they are pumped directly in and blended. Functional powders like caffeine and taurine are carefully weighed and added in controlled sequences to ensure complete dissolution without clumping. B vitamins, which are sensitive to heat, are typically added later in the process to preserve potency. The plant extracts, if used, are measured and incorporated at specific points, often emulsified to ensure they disperse evenly throughout the drink. Flavor concentrates, which can be highly potent, are metered into the mix using precision dosing pumps. These concentrates often contain a mixture of flavor oils, sweeteners, and acids in a stable base that integrates easily into the water-sugar matrix. Because Monster produces a wide variety of flavors, the plant must be capable of switching from one concentrate to another with minimal downtime. A challenge that requires clean-in-place systems to flush and sanitize mixing tanks and pipelines between batches. Once the syrup is fully blended, it is tested in the quality control lab for sweetness, acidity, caffeine content, and flavor profile. The lab team uses sensory analysis alongside instrumental testing to ensure the mixture matches the established standard. Only when it passes these checks is it moved forward. The next stage is dilution and carbonation. The concentrated syrup is blended with additional purified water in large batch tanks to reach the target formulation for the finished drink. This diluted beverage is chilled to near freezing temperatures to maximize the solubility of carbon dioxide during carbonation. The chilled liquid enters a carbonator, where CO2 is injected under high pressure and mixed through fine diffusers or inline mixers. The carbonation level is closely controlled. Too little, and the drink will taste flat. Too much, and it will foam excessively during filling. Once carbonated, the beverage moves immediately to the filling lines. Monster Energy is almost always packaged in aluminum cans, chosen for their lightweight, barrier properties, and recyclability. These cans arrive at the plant in massive pallets of unfilled containers, often printed with Monster's signature claw mark logo and variant-specific graphics. Before filling, each can is inverted and passed through a rinser, which uses either deionized water or ionized air to remove any dust or particles. The cans travel into high-speed rotary filling machines where they are filled from the bottom up to reduce foaming and preserve carbonation. Each filler head dispenses an exact volume, ensuring every can meets legal net content requirements. Immediately after filling, the cans pass into a seaming machine, where an aluminum lid is placed on top and mechanically rolled into place to form a double seam that locks the contents in airtight. This seaming process is a critical control point. Improperly sealed cans can lose carbonation or leak, so seamer performance is constantly monitored. Sealed cans are inverted briefly so that the liquid inside can contact the underside of the lid, which acts as a quick sterilization step. Depending on the plant's process, the cans may then undergo tunnel pasteurization. Moving through a heated water spray tunnel that raises the beverage temperature for a specific time to kill any microorganisms. Or may rely on aseptic filling techniques that eliminate the need for heat treatment. Once pasteurized or otherwise stabilized, the cans are cooled rapidly to prevent heat damage to vitamins and flavors. They then pass through a series of inspection systems. Automated vision cameras check for dents, damaged seams, or incorrect graphics. Check weighers ensure that each can contains the correct amount of product, and any deviation triggers an automatic rejection. Many lines also incorporate inline gas analysis to confirm carbonation levels in the finished product. The approved cans move into the secondary packaging area, where they are grouped into multi-packs. This may involve cardboard carriers, shrink-wrapped bundles, or trays depending on the market. Automated packers arrange the cans in the correct pattern, wrap or enclose them, and send them toward the case packing stage. Here, multi-packs are loaded into corrugated shipping cartons, which are sealed, coated with batch and date information, and stacked by robotic palletizers. Pallets are wrapped in stretch film to secure the load and sent to the warehouse for storage. Even though Monster Energy is shelf-stable at room temperature, it is generally stored in cool, dry conditions to maintain flavor and carbonation quality. From the warehouse, products move through distribution networks to retail shelves worldwide. Behind all of these steps is a rigorous quality control program. The production team pulls samples at every stage: syrup preparation, dilution, carbonation, filling, and post-packaging to confirm compliance with product specifications. Analytical labs test for caffeine content, sugar level, vitamin potency, pH, and carbonation. Microbiological testing ensures that no spoilage organisms are present. Sensory panels evaluate taste, aroma, and mouthfeel to maintain brand consistency. The machinery that makes this possible is heavily automated. Operators work from control panels in climate-controlled rooms, monitoring temperatures, pressures, flow rates, and carbonation levels via touchscreen interfaces. Programmable logic controllers coordinate the entire process, from mixing through palletizing, and sensors throughout the plant send real-time feedback. This automation allows Monster to produce enormous volumes with minimal downtime, while meeting strict safety and quality standards. Sustainability considerations are increasingly built into Monster's operations. Aluminum cans are highly recyclable, and many suppliers provide them with a significant proportion of recycled content. Water purification systems are designed to recover and reuse as much water as possible in non-product applications like cooling or cleaning. Heat from pasteurization is often recovered and used to preheat water for syrup preparation, reducing energy demands. Transportation logistics are optimized to reduce emissions, and some plants have moved towards renewable energy sources for part of their power. What is most striking about Monster Energy production is its consistency. The brand's image may be chaotic and wild, but the drink inside is the product of careful, repeatable processes that leave nothing to chance. Every step is measured, every variable tracked, every can inspected, ensuring that when a consumer pops the tab and hears that sharp hiss of carbonation, they get exactly the flavor, mouthfeel, and energy hit they expect, whether they bought it in a gas station in California or a convenience store in Seoul. The making of a can of Celsius Energy is a study in a modern beverage manufacturing where health-focused marketing meets industrial-scale precision. Although the drink is promoted as a fitness or metabolism-boosting energy beverage, the underlying production process is much like that of other carbonated functional drinks. A carefully balanced formula of water, sweeteners, active ingredients, and flavors blended, carbonated, and packaged under conditions designed to maintain purity, consistency, and shelf stability across millions of units. It begins with the most abundant ingredient, water. Water quality is paramount in Celsius production because any dissolved minerals, organic matter, or off flavors could interfere with the delicate flavor balance and the stability of the added functional ingredients. Purification is achieved through a series of treatments. First, the incoming water is screened through coarse filters to remove particles. Activated carbon filters then strip out chlorine, residual odors, and organic compounds. Reverse osmosis membranes reduce dissolved solids to extremely low levels, creating a neutral base. Finally, ultraviolet light or ozonation is applied to sterilize the water before it enters the formulation tanks. Once the water supply is ready, the functional and flavor ingredients that distinguish Celsius are prepared. Unlike traditional energy drinks that lean heavily on sugar and caffeine alone, Celsius incorporates a blend of caffeine from both synthetic and natural sources, such as green tea extract and guarana seed extract. It also features taurine, B vitamins, vitamin C, and in many varieties, additional plant extracts such as ginger root extract for a warming, metabolism-supporting effect. Some variants are sweetened with cane sugar, while many zero sugar options use non-nutritive sweeteners like sucralose or stevia extract. Acids like citric acid and malic acid are used to balance the flavor profile and help preserve freshness, while natural flavors, often fruit-based, create the distinct taste of each variety from sparkling orange to peach vibe. The first major step in production is creating the base concentrate or syrup. This happens in large stainless steel mixing vessels equipped with high shear agitators or propeller mixers to ensure complete dispersion of both solids and liquids. For sugar-containing variants, crystalline sugar is metered into the purified water and dissolved at a controlled temperature to speed up the process without causing caramelization. If the formula calls for 0-calorie sweeteners, these are introduced in microgram-precise quantities via automated dosing systems, as their sweetness intensity is many times greater than that of sugar. Functional powders, such as caffeine, taurine, and vitamin C, are weighed with laboratory-grade scales before being added. Plant extracts often arrive as liquid concentrates or fine powders and may require pre-dissolution in a small amount of water or glycerin to ensure they blend smoothly without clumping. For heat-sensitive ingredients like vitamin C, addition occurs towards the end of mixing to minimize degradation. Throughout this stage, the pH is monitored and adjusted as needed, since certain active compounds are more stable within specific acidity ranges. Once all solids are dissolved and liquids are homogenized, flavoring compounds are introduced. These may be natural fruit essences, essential oils, or compounded flavors from specialist suppliers. The flavoring process is highly sensitive. Even slight, over, or underdosing can shift the sensory profile away from the established standard. The completed syrup is sampled and sent to the in-house quality control laboratory for analysis. There, technicians measure sugar concentration, acidity, caffeine content, and other activities, and conduct sensory evaluations to confirm taste matches the reference profile. After passing these checks, the syrup is diluted with more purified water to the final formulation strength in large batch tanks. At this stage, the beverage is chilled to near freezing temperatures in preparation for carbonation. Carbonation is one of the signature sensory features of Celsius's sparkling varieties, and it is carried out with precise control over dissolved CO2 content. The chilled liquid flows into a carbonation unit where carbon dioxide gas is injected under pressure, dissolving evenly into the liquid. The goal is to achieve a crisp, sparkling mouthfeel without excessive foam that could cause filling issues. From the carbonator, the beverage is pumped directly to the filling lines. Celsius is typically packaged in slim aluminum cans, often the 12-ounce or 355 milliliter size, chosen for their portability, shelf life stability, and recyclability. The empty cans arrive at the plant in palletized stacks and are fed onto conveyors. Before filling, they undergo a rinse using ionized air or deionized water to remove any dust or particles. The cleaned cans are inverted, then righted, and sent into the filling carousel. The filling process operates at high speed, often hundreds of cans per minute, and is done under conditions that protect carbonation. Each filler head dispenses an exact volume from the bottom up to reduce turbulence. Immediately after filling, the cans move into a seaming machine, where an aluminum lid is placed on each and mechanically crimped to form an airtight seal. This seam is a critical element of the can's integrity, and seaming stations are regularly checked with seam micrometers to verify proper formation. Sealed cans may pass through a pasteurization tunnel, depending on the plant's preferred stability method. In pasteurization, the cans travel along a conveyor under sprays of hot water that raise the internal beverage temperature to a specific target for a defined time, killing any potential microorganisms. Afterward, the cans are cooled quickly to protect heat-sensitive nutrients. In some plants, aseptic filling technology is used instead, allowing the drink to be filled into sterilized cans without the need for post-fill heat treatment, which can better preserve delicate flavors and vitamins. Once cooled, the cans pass through a series of inspection systems. Vision systems scan for dents, label defects, or improper graphics. Check weighers ensure the net content is correct, and any can outside the tolerance is automatically rejected. Inline gas analyzers may measure CO2 content to confirm carbonation consistency. Approved cans enter the secondary packaging stage, where they are grouped into multi-can packs. Cardboard sleeves, shrink film, or tray packs are applied depending on the distribution plan. Multi-packs are collated into corrugated shipping cases, which are sealed with glue or tape and printed with batch codes for traceability. Robotic palletizers stack these cases onto pallets in stable patterns, after which the pallets are wrapped in stretch film to secure them for transport. The finished pallets move into climate-controlled warehouse storage. Celsius products are shelf-stable, but temperature control helps maintain flavor, carbonation, and nutrient stability over the shelf life. From here, pallets are shipped to distributors, retailers, and online fulfillment centers worldwide. Throughout this process, quality control is constant. Samples from each batch are tested for caffeine level, vitamin potency, flavor accuracy, pH, and carbonation before release. Microbiological tests ensure no spoilage organisms are present. Sensory panels evaluate the finished drink for mouthfeel, aftertaste, and aroma, comparing it to the brand standard. Because Celsius positions itself in the better-for-you beverage category, consistency in active ingredient content is especially critical, and certificates of analysis often accompany each production run. Behind the scenes, this is all enabled by a network of highly automated equipment controlled by programmable logic controllers. Operators monitor the process from control stations, adjusting parameters like mixing speed, carbonation pressure, or filler settings as needed. The plant's clean-in-place systems allow tanks, pipelines, and fillers to be washed and sanitized automatically between batches. ensuring hygiene without extended downtime. Sustainability is an increasing focus in Celsius production. Aluminum cans are infinitely recyclable, and many suppliers now provide cans with a high percentage of recycled content. Plants work to reduce water use in cleaning and cooling, recover heat from pasteurization to preheat processed water, and optimize transport routes to cut emissions. Some facilities integrate renewable energy into their operations, such as solar panels or purchase agreements for green electricity. What makes the Celsius production process interesting is the careful balance between functional beverage science and mass-market beverage engineering. While the plant extracts and nutrient additions require precise handling to maintain potency and stability, the large-scale manufacturing environment demands speed and efficiency. The result is a beverage that can deliver consistent taste, carbonation, and nutritional content across millions of cans, while supporting the brand's positioning as a lifestyle-oriented, health-conscious energy drink. The production of Starbucks products, particularly its packaged coffee offerings that end up in grocery stores, retail outlets, and international supply chains, begins long before a single bean is roasted. The entire process is built on one foundational element: green coffee sourcing. Starbucks, known for its commitment to quality and consistency, manages one of the most tightly controlled and globalized green coffee sourcing operations in the food and beverage industry. This first phase, the pre-roasting segment, is where the company sets the tone for every cup of coffee or bottled product it will eventually serve. And it's here we begin our highly detailed step-by-step journey. The green coffee sourcing process starts at origin in the tropical coffee-growing regions that straddle the equator, primarily Latin America, East Africa, and Southeast Asia. Starbucks primarily uses Arabica beans due to their more nuanced flavor profiles compared to the hardier but less complex Robusta variety. Within the Arabica family, beans are selected based on elevation, soil composition, rainfall, and harvest timing. Starbucks maintains long-standing relationships with coffee growers, cooperatives, and export mills in countries like Colombia, Ethiopia, Guatemala, Indonesia, Brazil, and Rwanda. But it's not as simple as ordering beans in bulk and having them shipped. Starbucks uses a proprietary set of sourcing standards known as Coffee and Farmer Equity Practices. These standards are not only a requirement for suppliers to be eligible, but also a multi-layered auditing framework. Cafe practices address 4 critical areas: product quality, social responsibility, environmental leadership, and economic transparency. Every farm or co-op that sells beans to Starbucks must pass rigorous inspections in these categories, many of which are carried out by third-party auditors trained in agricultural and labor practices. Once a farm or producer is approved under cafe practices, the beans are harvested, typically by hand. Hand-picking ensures that only ripe coffee cherries are selected, an essential factor in achieving flavor consistency in the final roast. These cherries are then processed at or near the farm using either the washed method. The washed method involves removing the pulp and fermenting the beans to eliminate the mucilage before drying, producing a cleaner, brighter flavor. The natural method dries the entire cherry and imparts a fruitier, heavier profile. The method used depends on the country, the farmer's infrastructure, and the target flavor profile desired by Starbucks blending teams. Once processed, the green beans are dried to a specific moisture content, usually between 10% and 12%, and stored in parchment until they are ready for export. Before leaving the origin country, the beans undergo a final hulling process to remove the parchment layer. At this stage, Starbucks' quality assurance teams at origin perform multiple assessments. These include physical evaluations and cupping, an industry-standard tasting method. Starbucks QA cuppers evaluate the green coffee on attributes like acidity, body, balance, sweetness, and aftertaste. Only those lots that meet Starbucks' sensory and structural requirements are approved for shipment. Approved beans are then packed into multi-layered jute bags with protective liners or into GrainPro plastic bags that guard against moisture and pests during transit. Each bag is tagged with a traceable barcode or lot number, which connects it to a digital database. This data includes not just the country and region of origin, but the exact farm or cooperative, harvest date, processing method, and quality score. This traceability is critical, not just for transparency and accountability, but also for quality replication year after year. Now begins the logistics phase. Starbucks contracts with specialized freight companies that understand the requirements of green coffee shipping. These beans are incredibly sensitive to temperature and humidity, even in raw form. A single exposure to high heat or excess moisture during transit can cause mold growth or flavor degradation. The beans are typically transported in temperature-stabilized shipping containers. If traveling by sea, the containers are outfitted with humidity control packs and dehumidifying systems. If air freight is used, the bags are carefully palletized, shrink-wrapped, and tagged with sensors that monitor environmental conditions throughout the journey. Upon arrival at one of Starbucks' roasting and manufacturing facilities, such as those located in York, Pennsylvania, Augusta, Georgia, Sandy Run, South Carolina, or Amsterdam, Netherlands, the green beans are unloaded, inspected, and entered into the factory's inventory management system. Before any production begins, each new shipment undergoes additional quality control. Samples from each bag or container are pulled and brought into the sensory lab. There, certified coffee graders perform cupping again, this time to ensure no quality loss occurred in transit. Moisture content, bean uniformity, and fragrance are retested. Beans that pass, these checks are tagged and routed to storage silos within the facility. These silos are food-grade, airtight steel vessels with internal climate regulation. Beans are stored based on variety, region, and intended blend. For example, Latin American beans destined for Starbucks blonde roast will be siloed separately from Ethiopian beans used in Starbucks Reserve offerings. Every silo is equipped with moisture sensors, thermometers, and pneumatic conveyor links, allowing operators to pull precise quantities for each roast batch according to master recipes. Before roasting can begin, beans are weighed into batches according to a specific ratio, depending on the blend being produced. Starbucks maintains an extensive library of proprietary blends, each with precise formulas. Some are single origin, where only one type of bean is used, while others, like Pike Place Roast or Espresso Roast, combine beans from multiple origins. Each blend is documented in the factory's recipe management software, which automatically calculates the needed amount of each component down to the gram and interfaces with weigh-scale systems to ensure accuracy. At this point, the beans are ready for roasting, but that process is highly intricate and deserves its own full analysis. Starbucks does not simply roast coffee by applying heat until the beans turn brown. The next step involves drum roasters, roast curves, heat profiling, airflow modulation, and real-time chemical transformation monitoring that will take the green coffee and convert it into the rich, aromatic, deeply flavored roasted beans that Starbucks is known for worldwide. With the green coffee beans now housed in precision-monitored silos and organized by blend formulation, the next phase of Starbucks' industrial production process transitions into what is often regarded as the heart of the entire operation: roasting. This stage is where the true transformation begins. The raw, pale green beans, earthy, grassy, and flavorless in their original state, are subjected to meticulously calibrated heat treatments that unlock their signature color, aroma, body, and complexity. Starbucks takes this phase extremely seriously, investing in proprietary roast profiles, customized equipment, and a multi-layered monitoring system to ensure that every batch matches the company's highly specific taste standards. The roasting process begins when a batch of green beans is called for from the storage silos. These silos are directly connected to the roasting equipment via stainless steel pneumatic transfer tubes. When an operator initiates a roast cycle, a preset quantity of beans, anywhere from 100 to 600 kilograms, depending on the size of the roaster, is discharged from the silo and transported through vacuum-sealed lines to the roaster's holding hopper. Here, the beans are pre-weighed on industrial platform scales connected to the plant's central production database, ensuring the exact quantity is delivered as dictated by the roast formula for that specific product, whether it's French roast, Pike Place, Sumatra, or espresso. Starbucks uses drum roasters for most of its large-scale production. These roasters consist of a rotating steel drum with an internal blade assembly that keeps the beans in constant motion. This ensures even exposure to heat as the drum is gradually raised to operating temperature, typically ranging between 190 degrees Celsius and 240 degrees Celsius, depending on the roast level. Lighter roasts, such as blonde roast, are roasted to lower final temperatures, while darker roasts, like French or Italian, require longer exposure and higher terminal heat. The roasting process follows a specific curve known as a roast profile. This is a data-driven graph that plots time against temperature, representing how heat is applied across the roast cycle. Starbucks profiles are proprietary and tightly controlled, with each product requiring a unique curve to deliver its intended flavor profile. These curves are not linear. They involve temperature ramps, plateaus, and even controlled dips. The initial drying phase lasts for several minutes, during which moisture is driven out of the bean. This is followed by the Maillard reaction phase, where sugars and amino acids begin to react, producing the rich brown coloration and the first wave of complex aromas. The most critical moment in roasting is known as first crack. This is when internal pressure in the bean causes it to physically crack open, producing an audible popping sound, much like popcorn. This marks a key transformation in bean chemistry. Starbucks roast operators listen for this moment, using audio sensors and thermal feedback to identify it precisely. Lighter roasts may be completed shortly after first crack, while medium and dark roasts continue through the development phase, where oils begin to emerge on the surface and flavor compounds deepen. Throughout this process, the roaster's control panel displays live data for bean temperature, exhaust temperature, airflow rate, and drum speed. The system is equipped with PID controllers and data logging software that feed into the factory's centralized SCADA system. Every roast is archived digitally, allowing Starbucks to recreate identical roast profiles across facilities on different continents, ensuring global consistency. Once the beans reach their designated roast level, they are immediately discharged from the drum into a cooling tray located below the roaster. This tray contains a rotating arm assembly that stirs the beans, while powerful fans blow ambient or chilled air upward from perforated grates below. Rapid cooling is essential to halt the roasting process and lock in the intended flavor and roast depth. If the beans are allowed to remain hot too long, they may bake, resulting in a flat, dull cup profile. The entire roasting to cooling process for a batch of coffee typically takes between 10 and 15 minutes, depending on the desired roast level and bean origin. Once cooled, the roasted beans are conveyed into degassing hoppers, stainless steel holding vessels, where the coffee rests for a short period, usually 12 to 24 hours. This rest period is necessary to allow CO2, a natural byproduct of roasting, to escape. If roasted beans are packaged too soon, the trapped gas can compromise packaging seals or even cause bags to inflate and rupture. However, some CO2 is desirable, especially for brewing freshness, so the timing of degassing must be carefully controlled. During this resting period, samples of each roast batch are collected and sent to the on-site sensory lab. Here, Trained cupping teams evaluate the beans using controlled brewing and tasting protocols. They assess key attributes like aroma, acidity, balance, mouthfeel, finish, and overall quality compared to Starbucks' master profile for that roast. Cupping is performed blind and in duplicate to eliminate bias and ensure accuracy. If a batch falls outside of the acceptable range, it may be blended with other batches to correct the profile, used for internal consumption, or in rare cases, discarded. Once a roast batch passes quality inspection, it is routed towards the grinding and packaging area. Some products, like whole bean offerings, will skip the grinding stage entirely, while others destined for ground coffee bags or capsules will be milled using precision grinders. These machines are fitted with hardened steel burrs or rollers that crush the beans to an exact particle size distribution. Starbucks defines specific grind profiles depending on brewing method. For example, drip coffee grind is coarser than espresso grind, and French press is coarser still. Grinding is a highly sensitive operation. During the process, friction from the burrs generates heat, which can degrade volatile aromatics if not carefully controlled. To counter this, industrial grinders are equipped with chilled air systems and thermocouple sensors that regulate burr temperature and prevent overheating. In many facilities, grinding is conducted in a temperature-controlled room or during cooler hours of the day to preserve freshness. As soon as the coffee is ground, it moves to packaging, often through vacuum-sealed transfer tubes that prevent oxidation. The packaging stage is designed to preserve flavor and aroma while ensuring shelf stability. Starbucks uses multi-layer barrier films for its ground coffee products. These films include aluminum or metallized polyester layers that block oxygen and moisture. Many packages are fitted with one-way degassing valves that allow CO2 to escape without letting oxygen in, protecting the coffee's integrity while preventing package ballooning. Packaging machinery includes vertical form fill seal systems for smaller bags and horizontal form fill seal machines for pillow packs or multi-packs. Each package is filled to a specific weight, sealed, and coded with production data, including roast date, location, shift, and lot number. High-speed check weighers and vision systems verify fill accuracy, seal integrity, and barcode clarity. Any package that fails inspection is automatically diverted off the line for rework. After packaging, the coffee products are grouped into cases and transferred to automated case packers and palletizers. Pallets are wrapped and labeled, then stored in temperature-controlled warehouses before shipping. These final steps, inventory control, cold chain monitoring, and outbound logistics, are critical to ensure the roasted Starbucks product reaches distribution centers and retail shelves around the world in optimal condition. With the coffee beans now expertly roasted, cooled, rested, and either packaged whole or ground and sealed, Starbucks' industrial production extends into another critical manufacturing domain, the preparation of its ready-to-drink beverages. These include bottled frappuccinos, chilled espresso drinks, cold brews, and dairy-based coffee blends. These products are not created in the same facilities that handle roasting and bagging. Instead, Starbucks partners with specialized beverage manufacturing facilities. Many cooperated with industry leaders like PepsiCo through the North American Coffee Partnership to manage this high-volume cold fill production. This stage involves liquid formulation, blending, thermal processing, homogenization, and sterile packaging under rigid food safety standards. The process begins with the formulation of the beverage base. For a bottled frappuccino, for example, this includes several core ingredients: brewed coffee extract, filtered water, sugar or corn syrup, dairy or dairy alternatives, stabilizers, and natural or artificial flavorings like vanilla, caramel, or mocha. Each component must be handled separately with precision before it's brought into the blending system. Coffee extract is typically delivered in concentrated form, produced by either brewing Starbucks beans at scale or using advanced extraction methods like cold concentrate percolation or high-pressure brewing. This extract arrives in refrigerated, food-grade totes or tanker trucks, depending on batch size. Upon arrival, it is sampled, analyzed for strength, and approved by the on-site quality control team before entering the liquid ingredient holding tanks. Simultaneously, dairy components such as milk and cream are received through chilled pipelines or aseptic bag-in-box systems. Dairy intake systems in Starbucks RTD plants are equipped with plate heat exchangers to quickly chill and store milk at temperatures below 4 degrees Celsius to maintain freshness and prevent bacterial growth. If using shelf-stable milk or UHT-treated dairy, the plant will still hold the product under cold storage until use. For plant-based SKUs, oat milk, almond milk, or soy milk are stored and handled in similar systems, albeit through dedicated lines to avoid allergen cross-contamination. Sweeteners and stabilizers such as sugar, corn syrup solids, carrageenan, cellulose gum, and pectin are weighed and pre-mixed in separate tanks. Starbucks beverages are engineered not just for taste, but for texture, mouthfeel, and visual consistency, especially in cream-based products like bottled mochas and vanilla frappuccinos. The stabilizers help suspend coffee solids, prevent dairy separation, and ensure the beverage maintains a smooth, homogeneous appearance on shelf, even after weeks or months in cold chain storage. All of these components, coffee extract, dairy or alternative milk, sweeteners, water, and flavor compounds, are brought together in the blending system. This usually consists of large stainless steel jacketed mixing tanks ranging from 1,000 to 5,000 litres. Each tank is equipped with an internal agitator, a bottom-mounted high-shear mixer, and in some cases, inline emulsifiers or homogenizers to ensure all elements are fully integrated. Tanks are fitted with load cells and flow meters, enabling automated dosing of each ingredient according to pre-programmed batch recipes. The blending system is monitored via a central control unit, typically a PLC-connected touchscreen interface that displays real-time values for temperature, mixing speed, pH, and ingredient flow. Operators can monitor the tank's temperature curve, the shear level during mixing, and the dwell time of each phase. In a typical Starbucks RTD batch, the blending cycle lasts between 30 and 60 minutes. During this time, inline sensors monitor turbidity, Brix, and viscosity. Samples are taken periodically to verify pH, flavor intensity, and microbial load before the batch is cleared for downstream processing. Once the beverage blend is complete and validated, the next stage is thermal processing. Most Starbucks RTD beverages are pasteurized using high-temperature, short-time systems, which allow for rapid heat treatment without compromising taste or texture. In HTST, the product is pumped through a heat exchanger that raises the liquid temperature to 85 degrees Celsius to 95 degrees Celsius for 15 to 30 seconds, then rapidly cools it to filling temperature, usually between 4 degrees Celsius and 10 degrees Celsius for cold fill lines, or slightly higher for hot fill bottles. This process effectively destroys any pathogenic microbes while preserving the coffee's aroma and flavor. Some facilities use ultra-high temperature processing for shelf-stable lines, allowing the product to remain unrefrigerated until opened. In UHT, the beverage is flash heated to temperatures up to 140 degrees Celsius for just a few seconds, then cooled quickly before packaging. The decision between HTST and UHT depends on the specific product's shelf life goals, packaging type, and distribution model. Immediately following thermal processing, the beverage passes through an inline homogenizer. This device applies intense pressure, often in excess of 2000 psi, to the liquid through a narrow valve, breaking down fat globules and suspended solids into microparticles. This step is critical for emulsion stability, preventing the cream from separating from the coffee or the flavor oils from rising to the surface. Homogenization also improves mouthfeel, making the beverage taste creamier and smoother. From here, the liquid is conveyed to the filling system. Starbucks RTD products are filled into a variety of package types: PET bottles, glass bottles, aluminum cans, and aseptic cartons. Each format requires its own dedicated filling and sealing system. For bottled frappuccinos, a cold fill rotary filler is typically used. This high-speed machine feeds sterilized bottles onto a rotating platform, where they are filled by gravity or volumetric fillers to exact fill levels. Immediately afterward, caps are applied, using steam-assisted capping heads to ensure a vacuum-tight seal and tamper resistance. Cans and cartons are filled on their respective lines, cartons often using form-fill-seal machines that shape the container, fill it, and seal the top in one continuous motion. All packages pass through automated detection systems that verify fill levels using weight sensors, check cap placement with vision systems, and scan barcodes to confirm packaging accuracy. Reject mechanisms immediately remove any container that fails these criteria. The filled beverages are then passed through a secondary cooling tunnel or refrigerated spiral conveyor that ensures they reach their final holding temperature before entering the packaging area. Depending on the product, this may be as low as 2 degrees Celsius, especially for refrigerated drinks destined for grocery and convenience store cold vaults. Once cooled, the individual containers are collected into multi-packs, shrink-wrapped, and placed into branded cartons. These cartons are then palletized by robotic arms and wrapped with plastic film. Each pallet is labeled with a unique identifier, linking it to the specific batch number, production date, filler line, and formulation ID. All of this information is uploaded into the factory's ERP system, providing full traceability from bean to bottle. Before any shipment is cleared, final product samples are pulled from each pallet for comprehensive testing. These include microbial testing, shelf stability stress tests, and sensory evaluations by trained panels. Only after all tests are passed are pallets released into refrigerated distribution channels for delivery to retail partners, Starbucks cafes, or direct-to-consumer platforms. From formulation and blending to pasteurization, homogenization, and ultra-clean packaging, this RTD production phase represents one of the most technologically advanced parts of Starbucks' global supply chain. It's where liquid meets logistics, combining industrial food science with tight controls over quality, taste, and branding. Every chilled bottle or can represents thousands of interconnected variables managed with absolute precision to deliver a consistent, enjoyable Starbucks experience anywhere in the world. With Starbucks ready-to-drink beverages now filled, sealed, chilled, and palletized, the focus shifts to the final, but no less complex, elements of factory operations. Sustainability integration, byproduct management, batch auditing, and outbound logistics. While the product may appear finished at this stage, the systems behind its release are still active, ensuring every bottle or can shipped reflects the brand's uncompromising quality, environmental responsibility, and traceability. One major component of this final phase is waste stream management. Every Starbucks beverage production facility is designed to minimize waste and make use of byproducts wherever possible. Coffee grounds remaining from extract production are collected and either sent to composting facilities, transformed into animal feed, or, in more advanced plants, used as biomass fuel to generate energy. Spent dairy materials or cleaning water are filtered and treated through on-site wastewater management systems, often returning grey water to municipal treatment plants within strict pH and chemical parameters. Packaging waste, including edge trims from shrink-wrap film, carton misprints, and PET bottle scrap, is separated and sent to in-factory compactors and balers. These bales are transported to certified recyclers for reprocessing. Starbucks has implemented programs at several manufacturing locations that convert unrecyclable soft plastics into composite shipping pallets or building materials, helping close the loop on production materials. In parallel with waste management, quality auditing continues even after packaging. Randomly selected finished products are pulled from every batch and routed to a dedicated quality assurance lab within the facility. There, they undergo another round of microbiological testing, sensory analysis, packaging integrity checks, and accelerated aging simulations. These simulations might involve storing the product at elevated temperatures for several days or weeks to mimic what could happen during prolonged distribution delays. Any deviation in flavor, appearance, or microbial safety can trigger a hold on the entire batch while root causes are investigated. All data generated, from roast date to filler head temperature, from pallet wrap tension to microbial test results, is logged in the facility's centralized manufacturing execution system. This digital record ensures that any shipment can be traced back through every step of the factory process. If a product recall is ever initiated, these logs allow immediate identification of affected units by date, location, and even by hour of production. When cleared, the finished pallets are scheduled for outbound logistics. Route planning software, inventory analytics, and order data from Starbucks' retail and grocery distribution teams are combined to determine where each batch will go. Products destined for grocery stores enter the cold chain system, transported in refrigerated trucks with temperature logs monitored in real time. Others, such as shelf-stable offerings, are routed to ambient storage hubs or export terminals for international shipping. The production of Red Bull starts long before the filling lines come to life. It begins at the sourcing and logistics stage, where each raw material used in the drink is carefully specified, contracted, and verified to meet the company's global quality standards. Although the ingredient list appears relatively simple: water, sucrose, glucose, citric acid, carbon dioxide, caffeine, taurine, B vitamins, and flavorings, the level of control and traceability involved in acquiring each component is remarkably complex. We begin with the most abundant ingredient: water. Water makes up the vast majority of the product, and its quality is absolutely critical. Unlike municipal tap water used in smaller food and beverage operations, the water used in Red Bull production must conform to pharmaceutical-grade purity standards. This means it undergoes extensive filtration, mineral balancing, and microbiological testing before it ever reaches the mixing tanks. In most Red Bull factories, water is drawn from deep, protected aquifers or dedicated water sources that are tested daily. The water is pumped into on-site treatment plants where it first passes through coarse filtration to remove particulate matter like sand or debris. It is then passed through activated carbon filters to strip away chlorine, organic compounds, or any remaining trace contaminants that could affect taste or chemical stability. The next step is typically reverse osmosis, a membrane-based filtration system that removes dissolved solids at a molecular level. This process reduces the water to an ultra-clean base, free of minerals, microbes, or off flavors. Once the water is purified, it enters holding tanks constructed from polished stainless steel. These tanks are fitted with level sensors, CIP spray heads, and temperature regulation systems to maintain stability. Water is kept in motion using gentle agitators or circulation pumps to avoid stagnation and ensure readiness for blending. Meanwhile, the sugar content of Red Bull, derived from both sucrose and glucose, requires its own specialized preparation. Red Bull uses a combination of these two carbohydrates to create its sweet but not overly cloying flavor profile. These sugars are sourced from sugar beets and corn and arrive at the plant either in dry crystalline form or as concentrated syrups, depending on regional supply chains. In facilities that receive dry sugar, the ingredient is pneumatically conveyed from delivery trucks into sealed sugar silos. These silos are climate controlled to prevent moisture absorption and equipped with weight sensors to track inventory in real time. When ready for production, the sugar is transferred to large dissolving tanks where it is combined with hot, purified water and mixed using high shear agitators to create a uniform syrup. This syrup is passed through mesh filters to remove any undissolved particles, then sent to a holding tank where it is cooled and held under sterile conditions. For glucose syrup, the process is slightly different. Delivered in bulk liquid containers or tanker trucks, the syrup is pumped through heated, insulated lines to prevent crystallization during transfer. Inline flow meters and viscosity sensors are used to ensure consistency. Once in the storage tanks, the glucose syrup is sampled and tested for pH, sugar concentration, and microbial stability before being cleared for blending. Now comes taurine, one of the most distinctive and chemically sensitive ingredients in the formula. Taurine is an amino acid-like compound that plays a role in neurological development and cellular hydration. It is synthesized in pharmaceutical-grade chemical plants through a controlled reaction involving ethylene oxide and sodium bisulfite, resulting in a high-purity crystalline powder. Red Bull does not extract taurine from animal sources. It is entirely synthetically produced for purity and consistency. Taurine is delivered to the beverage plant in sealed drums or lined bags inside rigid totes. Upon arrival, each container is inspected and sampled. The contents are tested for purity using high-performance liquid chromatography and screened for heavy metals and microbial contamination. Once cleared, the powder is either stored in a dry room or moved directly to the batching area, where it is weighed with precision down to the gram using automated ingredient scales. Caffeine, another central functional ingredient, is handled with similar precision. Synthetic caffeine, which is chemically identical to naturally occurring caffeine, is the preferred form in most facilities due to its purity and consistency. It arrives in fine white powder form, packaged in airtight containers to prevent oxidation and contamination. Like taurine, caffeine is dosed in tightly controlled quantities. Too much, and the drink becomes bitter or risks regulatory violation. Too little, and the expected stimulant effect may be lost. B group vitamins, specifically niacin, pantothenic acid, vitamin B6, and vitamin B12, are delivered in stabilized powder form. These micronutrients are highly sensitive to heat, light, and oxygen, so they are packaged in light-blocking, nitrogen-flushed containers. They are stored in temperature-controlled rooms and only opened at the time of production. Dosing is managed using micro-feeding systems, capable of adding quantities in the milligram range with high accuracy. Citric acid, used to balance sweetness and enhance shelf life, is one of the more straightforward ingredients. It arrives in either crystalline or liquid form, depending on plant setup. Like the sugars, citric acid is dissolved or diluted in purified water, filtered, and then pumped into blending tanks using stainless steel sanitary piping. It is included not only for flavor, but also to regulate the final pH of the drink, which has an impact on microbial resistance and carbonation behavior. The final core ingredient, prepared before blending, is carbon dioxide. Although it's added at the end of the line during filling, CO2 must be stored on-site in large insulated tanks under high pressure. This gas is certified food grade and must meet stringent standards for purity and dryness. Impurities in the gas, such as hydrocarbons or sulfur compounds, can result in off flavors or affect carbonation stability. Inline purifiers and moisture traps ensure that the gas remains within specification as it travels to the carbonation units. At this stage, all the major ingredients have been separately received, prepared, filtered, and stored in secure holding tanks, each one monitored by a network of sensors and controlled through a centralized process control system. The factory is now ready to enter the next phase, the blending and batch formulation process, where the base liquid is built step by step from these prepared components under tightly monitored conditions. Inside the blending hall of a Red Bull manufacturing plant, massive stainless steel tanks, often tens of thousands of liters in capacity, stand ready to receive pre-prepared ingredients. Each of these tanks is built with industrial mixers at the base and along the walls, with baffles designed to eliminate dead zones and ensure even distribution of all ingredients once mixing begins. These aren't just glorified vats, they're engineered systems with flow sensors, agitation controllers, and automated dosing inlets. Blending starts with the base, purified water. A calibrated volume is pumped into the blending tank. From here, the sweetener solution is added. By this point, the sugar and glucose have been dissolved into a consistent syrup in separate vessels and passed through fine mesh filters to remove any undissolved particles. They're now gravity-fed or pumped into the main tank through metered valves, which record the exact volume added in real time. At this stage, the solution is still colorless, with a mild sweetness and a viscosity slightly thicker than water. Stirring begins slowly, just enough to encourage circulation without aerating the mixture prematurely. Once the sweet base is established, the functional ingredients are added in a very specific sequence. This isn't just for convenience, it's chemical. Caffeine, taurine, and vitamins each behave differently depending on the pH, temperature, and concentration of the liquid they're introduced into. To ensure even dissolution, caffeine is dosed in carefully, often pre-blended into a neutral, aqueous solution to avoid clumping. Taurine, being more soluble, can be introduced directly, but at a steady rate to avoid localized saturation. The temperature of the blend is strictly controlled during this entire process, typically kept between 10 degrees C and 15 degrees. Keeping the temperature low helps prevent degradation of the heat-sensitive components, especially the B vitamins, and also limits the risk of microbial growth. Inline cooling jackets on the tank walls help regulate this, while digital sensors constantly send data to the factory's main control panel. After the active ingredients are in and fully dissolved, the next step is homogenization. While Red Bull is a clear drink and doesn't have oil-based elements like some emulsified beverages, this process is still used to ensure complete molecular distribution. A high-speed rotor-stator mixer is activated to subject the liquid to intense shear forces, ensuring that no microclumps or undissolved pockets remain. Think of this as the industrial version of making sure your recipe has no lumps, but at a scale where a few unblended grams could ruin an entire batch worth millions of servings. Once homogenized, the blend is passed through a fine filter system, often absolute rated filters that remove particles down to the sub-micron level. This is the final polish of the beverage, ensuring not just clarity and texture, but also eliminating any particulate matter that could interfere with carbonation or filling equipment. Now, the finished liquid base is sent to a storage tank, often referred to as the balance tank, which feeds the carbonation system. At this stage, the liquid is still uncarbonated. Carbonation must be done with surgical accuracy, both in timing and in gas levels. Too early, and carbon dioxide can escape during filling. Too late, and the drink will feel flat. Before carbonation, the balance tank contents are degassed using a gentle vacuum system to remove any dissolved air from the blend, air that could interfere with carbonation or introduce unwanted oxygen into the final product, leading to flavor instability over time. Carbonation is introduced through a high-precision saturator. This device uses temperature, pressure, and turbulence to force carbon dioxide into the liquid. The lower the temperature, the more CO2 the liquid can absorb, so the beverage is chilled further just before entering the saturator. Inside the unit, The liquid flows in a turbulent spiral while pressurized CO2 is injected. Sensors monitor saturation levels down to fractions of a gram per liter, and the flow is fine-tuned via automated valves. Once carbonated, the beverage is immediately transferred to the filler line. No storage, no delay. At this point, any agitation or exposure to heat could cause gas to escape, so the tubing, valves, and tanks are all designed to reduce turbulence. The product is now ready to be introduced into cans. Filling lines in a Red Bull factory are among the fastest and most technologically advanced in the beverage industry. The cans themselves arrive at the plant in stacks of blank aluminum cylinders, unprinted or pre-printed depending on the factory setup. These cans are depalletized automatically and conveyed upright to the rinser station. Here, they're inverted and sprayed internally with deionized water or sterile air to remove dust or particulates. From the rinser, the cans travel on a conveyor to the filler. This machine uses a gravity or counter-pressure system to fill each can precisely while preserving carbonation. The can enters the fill station, is sealed around the top rim with a flexible gasket, and then filled from the bottom up with cold, pressurized beverage. Fill levels are controlled within a margin of plus 0.5 grams to ensure legal compliance with net content regulations and consistent customer experience. Immediately after filling, the can passes to the seamer, where a pre-formed aluminum lid, known as the end, is dropped onto the top and crimped into place. This creates an airtight seal. Seamers are some of the most mechanically intricate machines in the entire facility, operating at speeds of over 1,000 cans per minute while performing multiple precision operations in less than a second per unit. After sealing, the cans are rinsed externally to remove any spillage and pass through a drying tunnel. They then enter the inspection phase. Here, cameras and sensors verify the seal integrity, check fill levels using X-ray or gamma-ray detection, and inspect for dents, deformations, or labeling defects. Any can that fails inspection is automatically ejected from the line. Cans that pass all tests are conveyed to the packaging station. Depending on the market, cans are grouped in 4-packs, 6-packs, or full case trays. Robotic arms or mechanical pushers group the cans and slide them into shrink-wrap tunnels or cardboard sleeves. Once bundled, packs are palletized, either by layer robots or high-speed stackers, wrapped with stretch film and labeled with product codes, production date, and batch information. These pallets are now staged in a temperature-controlled warehouse, ready for distribution. The real-time tracking of every single ingredient, batch, fill date, and can code allows for full traceability from ingredient origin to final shipment. In the next section, we'll follow how those pallets move through the global distribution network and how Red Bull's quality assurance, shelf stability testing, and cold chain monitoring ensure that each can performs exactly as intended from Austria to Australia. With the Red Bull cans now filled, sealed, and packed onto pallets, the production process transitions into the next highly critical phase: post-production handling, distribution management, and long-term quality assurance. Although the drink is technically finished, the factory still bears significant responsibility for maintaining its integrity through storage, shipping, and shelf life. This phase involves coordinated warehouse systems, climate control, global logistics networks, and extensive quality monitoring procedures that extend well beyond the factory floor. All of it is designed to ensure that every can of Red Bull tastes and performs identically, whether it's consumed in Bangkok, Berlin, or Boston. Once the pallets are complete, they are conveyed from the packaging area into the outbound staging zone, a dedicated part of the facility built to manage finished goods. This area is laid out with barcode scanners, RFID readers, and automated warehouse software. Each pallet is scanned as it enters, recording not only the product type and production date, but also its batch code, can format, and destination market. This digital tracking ensures complete traceability of every pack produced. The system also flags any inventory that is out of rotation or that has not been cleared by the final quality audit. Pallets are stored in high bay racking systems that can reach 5 or 6 levels high. These racks are arranged to maximize airflow and minimize temperature variation, as environmental stability is critical for energy drinks. The warehouse is kept within a strict range of temperature, typically between 18 degrees C and 22 degrees C, and humidity under 60% to preserve carbonation, prevent packaging degradation, and protect flavor stability. Light exposure is minimized using tinted overhead fixtures or motion sensor lighting, since prolonged light can interact with the contents of clear or thin-walled aluminum containers, subtly affecting taste or causing internal discoloration. But before any pallet leaves the facility, it must be cleared through a final release protocol. This involves sampling from each production batch, typically 1 out of every few thousand units. These samples are sent to the in-house quality control laboratory for a battery of tests. Microbial testing is conducted to ensure that the beverage remains free from bacteria or yeast. Although Red Bull is not pasteurized, its low pH and high CO2 content provide natural protection, and the factory's sterile filling conditions act as a critical control point. Nonetheless, post-fill samples are incubated in climate-controlled chambers for 72 hours and checked for any microbial activity. Simultaneously, chemical stability tests are performed to verify that the concentrations of caffeine, taurine, sugars, acids, and vitamins are within tight tolerances. Each test is logged, reviewed, and signed off by senior lab technicians. Once the data passes review, the production batch is cleared for shipping. At this point, the factory releases the inventory into the hands of the logistics team, which organizes regional and international transportation. The Red Bull supply chain is designed around speed, efficiency, and protection. Because the drink is sold in more than 170 countries, it requires a global distribution system that can manage environmental variables, transit times, and regulatory differences across continents. Each factory or co-packing facility is paired with multiple logistics hubs, either operated directly or through third-party logistics providers, each specializing in cold chain monitoring, customs clearance, or last-mile delivery. Shipping conditions are tightly controlled. While Red Bull cans are shelf-stable and do not require refrigeration, they are sensitive to excessive heat and should not be exposed to prolonged freezing. Therefore, all transportation routes are mapped to avoid extreme temperature exposure. Trucks are preconditioned before loading, ensuring that their interior holds the correct temperature before the first pallet is moved in. During loading, factory staff monitor not just product count and pallet orientation, but also airflow paths and stacking height to ensure that cans are not crushed or deformed during transit. Each truck or container is equipped with temperature loggers and shock sensors. These devices record environmental data every few minutes and store it until offload. If a truck breaks down, or if the cargo passes through an area of extreme temperature fluctuation, the logs will show it. When the shipment arrives at its distribution center or regional warehouse, receiving teams will review the data. If it falls outside the acceptable range, the load may be held, inspected, or even rejected. This provides a full audit trail from the moment the product left the factory to its arrival at the next checkpoint. For international shipments, the process becomes even more complex. Export shipments must comply with country-specific food regulations. In some cases, ingredients must be declared differently. In others, labeling requirements vary. The factory works with regulatory teams to produce market-specific versions of the product, sometimes varying the language, caffeine content, or vitamin mix to meet local laws. Each international pallet is assigned a customs manifest, a certificate of analysis from the lab, and a temperature log that confirms it stayed within the specified range throughout the journey. Once Red Bull arrives at its destination warehouse, whether it's in Tokyo, Johannesburg, or Chicago, it enters a new round of inventory rotation and quality checks. Local distribution centers store the product under similar environmental controls, and the product is rotated using FIFO systems to minimize aging. While the drink has a long shelf life, usually around 18 months, Red Bull's internal standards aim to deliver most of its inventory to retailers within just a few weeks of production to ensure maximum freshness. Some pallets will be broken down into smaller loads and sent to large supermarket chains. Others are routed to gas stations, bars, vending machine operators, or e-commerce fulfillment centers. In each case, local merchandisers and sales teams monitor product placement, stocking practices, and display temperatures. Although Red Bull does not require refrigeration, many retailers choose to chill it for immediate consumption, and Red Bull provides branded refrigeration units to support this. At the store level, Red Bull continues to run random quality checks, known as in-market assessments. These include taste tests, packaging inspections, and code date verifications. Data from these assessments is sent back to the factory quality system and reviewed quarterly. If trends are observed, like subtle flavor degradation in warmer climates or denting during local transit, factory protocols are updated and packaging specifications may be revised. This feedback loop is critical to maintaining the uniform experience that Red Bull is known for globally. Even after the product has been sold, the process doesn't stop. Red Bull maintains traceability for every batch through lot codes printed on the bottom of each can. If a customer reports an issue, the quality team can pull that code, identify the exact production line, shift, and even the technician who oversaw that batch. While issues are rare, this system allows the company to investigate and resolve problems with precision, minimizing waste and protecting brand integrity. Beyond logistics and troubleshooting, the factory also conducts long-term aging tests. Retained samples from every production batch are stored under controlled conditions for 12 to 24 months. These samples are periodically tested for flavor consistency, vitamin retention, carbonation, and packaging durability. This helps inform decisions about shelf life labeling, new packaging materials, and product reformulation. Back at the plant, everything learned during distribution feeds into continuous improvement efforts. Engineers analyze transit shock data to refine pallet structures. Chemists review long-term flavor curves to tweak the balance of acids and preservatives. Operators attend refresher training sessions on fill line calibration, cap torque standards, and seaming pressure. The plant becomes not just a factory, but an evolving ecosystem of precision, designed to produce millions of cans with microscopic tolerance and global dependability. Inside Red Bull's production and R&D infrastructure, innovation continues quietly and continuously alongside the high-speed filling lines. While the mainstream drink is tightly standardized, parallel systems exist within the factory environment for development, testing, and controlled rollout of new variants, flavors, and formats. These operations are often confined to specialized pilot plants, small-scale, highly modular manufacturing lines where experimental recipes and new packaging concepts are trialed without disrupting the core production flow. These pilot lines mimic every critical phase of full-scale production, from batching to carbonation and filling, but at reduced volumes. Engineers can simulate the thermal and mechanical stresses of the full-size process, adjusting flow rates, temperature profiles, and equipment speeds to understand how small tweaks to formula or process could affect outcomes. Whether testing a sugar-free variation, a new flavor blend, or a limited edition can size, the data collected here determines what does and does not graduate to full factory rollout. Each new formula undergoes rigorous stress testing. Finished samples are subjected to cycles of heat, cold, vibration, and light exposure to simulate real-world transport and storage conditions. Flavor retention is tracked over time through sensory analysis and gas chromatography. Carbonation levels are monitored for stability across packaging types and temperatures. Packaging engineers assess how different aluminum can wall thicknesses or end configurations perform under pressure, especially when new recipes require modified CO2 saturation. If a variant clears all physical and chemical tests, the next step is consumer trials. In select cases, Red Bull collaborates with regional markets to test launch a new flavor or packaging size in a limited territory. These micro launches help measure demand, gather feedback, and identify operational issues before scaling up. Even then, these limited variants are often produced on flexible equipment lines reserved specifically for such runs, using interchangeable molds, modular filler heads, and smaller tank systems. Even small changes, like switching from a matte to a gloss label finish, require recalibration of the vision systems on the inspection line. Barcode scanners must be trained to detect label variations, and automated reject mechanisms must be tested to avoid false positives. This ensures no disruption in quality control, even when the product range temporarily expands. Back in the lab, teams also study ingredient interactions under extreme use scenarios. The production of sunflower oil in modern industrial facilities is a meticulously orchestrated process that transforms raw sunflower seeds into the clear, golden oil commonly used in cooking and food production. This journey begins with the careful selection and preparation of sunflower seeds, ensuring that only the highest quality seeds are processed to produce premium oil. Upon arrival at the processing plant, sunflower seeds are subjected to a rigorous cleaning regimen designed to remove a variety of impurities that may have been introduced during harvesting and transportation. This initial phase is critical, as foreign materials such as soil, stones, plant debris, and metal fragments can compromise the efficiency of the extraction process and the quality of the final product. The cleaning process typically involves several stages, each employing specialized equipment tailored to eliminate specific types of contaminants. The first line of defense in the cleaning operation is the magnetic separator. This device utilizes powerful magnets to attract and remove ferrous metal particles from the stream of sunflower seeds. Metal contaminants can originate from various sources, including harvesting equipment and transport containers, and their removal is essential to prevent damage to downstream processing machinery and to ensure product safety. The seeds pass over or through magnetic plates or drums, where metallic impurities are captured and separated from the bulk material. Following magnetic separation, the seeds proceed to vibrating sieves or screens. These machines consist of perforated plates or mesh screens that oscillate at high frequencies, effectively sorting the seeds based on size and shape. Larger impurities, such as sticks, leaves, and oversized debris, are unable to pass through the screen openings and are thus separated from the smaller, uniform sunflower seeds. The vibration intensity and screen aperture sizes are carefully calibrated to optimize the removal of unwanted materials, while minimizing the loss of viable seeds. To address the presence of denser contaminants like stones and clumps of soil, the cleaned seeds are then routed through destoners. Destoners operate on the principle of density separation, utilizing airflow and vibration to differentiate between heavier impurities and the lighter sunflower seeds. As the mixture is fed onto an inclined vibrating deck, air is blown through the material from below. The heavier stones resist the upward airflow and migrate to the higher end of the deck, where they are discharged, while the lighter seeds are carried by the vibration to the lower end for collection. This process effectively ensures that only clean seeds advance to the next stage of processing. After the comprehensive cleaning process, the sunflower seeds are ready for dehulling, also known as shelling. Sunflower seeds are encased in hard outer shells or hulls that constitute a significant portion of the seed's total weight. These hulls are low in oil content and can impede the extraction process if not removed. Therefore, dehulling is a crucial step aimed at increasing the efficiency of oil extraction and improving the quality of the resulting oil. The dehulling process begins with the conditioning of the seeds to facilitate the separation of the hulls from the kernels. Conditioning typically involves adjusting the moisture content of the seeds through controlled heating or humidification. Properly conditioned seeds have hulls that are more brittle and easier to crack, enhancing the effectiveness of the dehulling equipment. Once conditioned, the seeds are fed into dehulling machines, which employ mechanical forces to crack the hulls. One common type of dehuller is the centrifugal sheller, which uses a rotating impeller to hurl the seeds against a hard surface, causing the hulls to fracture upon impact. Another method involves the use of roller mills, where seeds pass between counter-rotating rollers that exert compressive and shear forces, breaking the hulls without damaging the kernels. The choice of dehulling equipment depends on factors such as seed variety, desired throughput, and specific plant configurations. Following the cracking of the hulls, the mixture of kernels and shell fragments undergoes a separation process to isolate the oil-rich kernels. This separation is typically achieved through a combination of aspiration and screening techniques. Aspiration involves the use of air streams to lift and remove the lighter hull fragments from the heavier kernels. The mixture is fed into an aspirator, where a controlled airflow lifts the less dense hulls away from the denser kernels, effectively segregating the two components. Screening may also be employed, utilizing vibrating screens with specific mesh sizes to further refine the separation based on particle size and shape. The efficiency of the dehulling and separation processes is paramount, as incomplete removal of hulls can lead to increased fiber content in the oil, affecting its clarity and stability. Moreover, residual hulls in the meal byproduct can diminish its nutritional value and marketability as animal feed. Therefore, processors often implement multiple passes through dehulling and separation equipment to achieve optimal results, balancing the trade-offs between processing time, energy consumption, and product quality. With the sunflower kernels now isolated and free from their hulls, they are ready to undergo further processing to extract the valuable oil contained within. The next stages involve mechanical pressing and/or solvent extraction, each with its own set of procedures and equipment designed to maximize oil yield and quality. These processes will be explored in detail in the subsequent sections, delving into the intricacies of transforming cleaned and dehulled sunflower seeds into the refined oil that reaches consumers worldwide. Now it's time to go into the core phase of sunflower oil manufacturing, the oil extraction process. This is where the golden liquid locked inside the sunflower kernels is separated and collected. The extraction phase typically uses one of two methods, or more commonly, a combination of both, for optimal oil recovery: mechanical pressing and solvent extraction. Each method has its own benefits and limitations, and modern sunflower oil factories are designed to seamlessly integrate these systems into a continuous, high-efficiency process that minimizes waste and maximizes yield. The first step in oil extraction is mechanical pressing, often referred to as expelling. In this process, the dehulled and cleaned sunflower kernels are conveyed into a series of screw presses, also known as oil expellers. These heavy-duty machines consist of a cylindrical barrel housing a rotating helical screw shaft. As the kernels are fed into the expeller from one end, the screw shaft compresses them with increasing pressure as they travel along the barrel. The space between the screw and the barrel gradually narrows, intensifying the pressure and causing the oil to be forced out through small perforations or slits in the barrel wall. This process is incredibly robust and continuous, with some industrial presses capable of handling several tons of seed per hour. However, mechanical pressing alone can only extract about 85% to 90% of the total oil content from sunflower seeds. The remaining 10% to 15% stays trapped in the pressed cake, a solid, fibrous byproduct that still contains a considerable amount of valuable oil. To retrieve this remaining oil and improve overall efficiency, factories employ solvent extraction. Before the solvent extraction phase begins, the pressed cake from the mechanical expeller must be properly prepared. This involves breaking the compacted cake into smaller, uniform pieces using a cake breaker or flaking mill. The flakes are then conveyed to a conditioning unit where they are heated to a specific temperature, usually between 60 to 80 degrees Celsius. This heating not only helps to soften the cell structure of the material, but also enhances the effectiveness of the solvent by improving oil solubility and fluidity. Once conditioned, the sunflower cake is fed into a continuous extractor, typically a horizontal rotary extractor or a loop extractor. In this large stainless steel apparatus, the cake is soaked with a food-grade solvent, most commonly hexane, which has an exceptional ability to dissolve oils. The cake moves slowly through the extractor on a perforated conveyor belt or through a series of baskets, while the solvent is sprayed from above and recirculated from below. As the hexane seeps through the material, it dissolves the residual oil, forming a solution known as micellar. This micellar, containing both oil and solvent, is then pumped out of the extractor and sent to a series of distillation units where the solvent is evaporated and recovered, leaving behind the crude sunflower oil. The evaporation process is conducted under vacuum and controlled heating conditions to ensure complete solvent recovery without degrading the oil. Simultaneously, the now oil-depleted cake, referred to as spent meal, is conveyed to a dissolventizing toaster. This equipment uses steam and indirect heat to remove any residual hexane from the meal, making it safe for use as high-protein animal feed. Next, let's look at the processing of crude sunflower oil, which, at this stage, is a deep amber liquid that contains several impurities, including free fatty acids, phospholipids, pigments, waxes, and trace metals. Though technically oil, this unrefined product is not yet suitable for cooking or bottling. It must be purified and stabilized through a multi-step refining process, which includes degumming, neutralization, bleaching, dewaxing, and deodorization. The first of these refining steps is degumming. In this phase, the crude oil is mixed with a small amount of water or a weak acid, such as citric or phosphoric acid. This causes the naturally occurring phospholipids, also known as gums, to become hydrated and coagulate into a heavier phase that can be separated through centrifugation. The removal of these gums is crucial because they can contribute to off flavors, reduce shelf life, and interfere with further refining stages. The centrifuges used here operate at extremely high speeds, up to 5,000 revolutions per minute, creating centrifugal forces strong enough to separate even microscopic droplets and particles. Once degummed, the oil is subjected to neutralization, where it is treated with a caustic soda solution to remove free fatty acids. These acids can contribute to rancidity and reduce the oil's stability, so their removal is vital for producing a high-quality, shelf-stable product. The soda reacts with the free fatty acids to form soap stock, which is then separated from the oil via another round of centrifugation. The soap stock may be further processed into industrial byproducts such as lubricants or fatty acid distillates, ensuring minimal waste. Now it's time for the bleaching phase. Despite its name, this stage does not involve any chlorine or harsh chemicals. Instead, the oil is mixed with an adsorbent clay material, often activated bleaching earth or acid-activated bentonite, that binds with pigments, trace metals, and other unwanted compounds. The mixture is then heated under vacuum and passed through a filtration system where the spent clay is removed, leaving behind a visibly lighter oil. The objective of this step is not only to improve the color, but also to remove pro-oxidants and residual contaminants that could impact the oil's flavor or stability. But up next is one of the most temperature-sensitive and critical steps: dewaxing. Sunflower oil naturally contains waxes that, while harmless, can cause cloudiness or sedimentation when the oil is refrigerated or stored at low temperatures. To ensure crystal clear oil, particularly for use in transparent bottles, the dewaxing process is implemented. The oil is cooled gradually in a crystallization tank to allow waxes to solidify, and then pass through chilling filters or plate and frame filter presses. The solidified waxes are captured by the filter media and removed, leaving the oil with improved cold stability and clarity. Finally, the last refining step is deodorization. This process removes volatile compounds, including aldehydes and ketones, that can impart undesirable flavors and odors to the oil. Deodorization is carried out in a high vacuum, high temperature distillation column where the oil is subjected to steam distillation at temperatures between 180 to 240 degrees Celsius. The high temperature causes the volatile substances to evaporate, and the vacuum ensures they are swiftly removed from the system. Modern deodorization systems include structured packing and multiple stripping trays that allow for efficient steam-oil contact with minimal thermal degradation of the oil. The end product of this exhaustive refining sequence is a brilliant, light yellow, odorless oil with a neutral flavor and excellent oxidative stability, qualities that make it ideal for cooking, frying, baking, and use in processed foods. The refined sunflower oil is now ready for bottling or bulk packaging, depending on its intended application, whether destined for supermarket shelves or as an ingredient in snack foods, margarine, or ready-to-eat meals. The oil's journey from seed to bottle is far from over. Now it's time to explore the next critical phase in the industrial sunflower oil production process, the packaging and distribution stage. After undergoing extensive cleaning, pressing, solvent extraction, and refining, the sunflower oil is now fully processed, brilliant in clarity, neutral in flavor, and stable for both cooking and long-term storage. But before it can reach consumers or be used by food manufacturers, the oil must pass through highly automated and carefully controlled packaging systems. These systems are designed to maintain product integrity, optimize shelf life, and meet regulatory and commercial requirements for both retail and industrial distribution. Once the refined sunflower oil leaves the deodorizer, it is pumped into large stainless steel holding tanks. These tanks are equipped with inert gas blanketing systems, typically using nitrogen, to prevent oxidative degradation of the oil. Even trace amounts of oxygen can initiate rancidity, so maintaining a low oxygen environment in storage is critical. The tanks are also thermally insulated and often jacketed for temperature control, maintaining the oil at a stable range of around 25 to 30 degrees Celsius. This ensures that the oil remains fluid and clear, preventing cloudiness that could otherwise form during cooler storage conditions. From these storage tanks, the oil is directed via stainless steel pipelines to the packaging area. The transfer lines are equipped with positive displacement pumps and high sensitivity flow meters to ensure precise, consistent delivery volumes. Before entering the filling systems, the oil passes through final filtration units, often made up of multi-layer stainless steel mesh or polymer filter cartridges to capture any microscopic particulates that may have entered during tank storage. This guarantees that only the cleanest, crystal clear oil reaches the packaging stage. The packaging line is often separated into two main tracks, one for retail-sized bottles, typically ranging from 500 milliliters to 5 liters, and another for bulk containers, such as 20-liter jerry cans, 200-liter drums, or 1,000-liter intermediate bulk containers for industrial clients. The retail packaging line begins with empty bottles being loaded onto a conveyor, either manually or through robotic depalletizers. These bottles are usually made from food-grade PET and are blow molded on-site or sourced from specialized suppliers. Before filling, every bottle passes through a bottle rinser, where a jet of filtered, compressed air or ozonated water is sprayed inside to remove any dust or particles. This ensures microbiological and particulate cleanliness before the oil is introduced. The cleaned bottles are then transferred to multi-head volumetric or gravimetric filling machines. These high-speed machines, capable of filling up to several hundred bottles per minute, are calibrated to extreme accuracy, ensuring every bottle contains the precise labeled volume, no more, no less. The filled bottles are immediately capped by rotary capping machines, which place and tighten tamper-evident screw caps or snap-fit closures. Some systems integrate induction sealing, where a foil liner inside the cap is sealed to the bottle mouth using electromagnetic energy. This creates an airtight, tamper-proof barrier that preserves freshness and prevents leakage during transit. After capping, bottles pass through labelers that apply pressure-sensitive or shrink-sleeve labels. These labels are printed with brand information, nutritional facts, batch codes, and expiration dates using high-speed inkjet or laser coders, allowing for complete traceability of every unit. Following labeling, bottles proceed through automated inspection systems equipped with cameras and sensors that verify fill levels, cap integrity, label alignment, and code legibility. Any non-compliant bottles are automatically rejected via pneumatic arms into separate bins for rework. Approved bottles continue along the line to automated cartoning and case packing stations, where robotic arms place them into cardboard cartons, followed by case sealing with hot melt glue or tape. For bulk packaging, a separate line handles large volume containers. These containers are positioned under filling nozzles that are often suspended from load cells to ensure accurate weight-based filling. Bulk fillers must also incorporate anti-foaming and venting mechanisms to prevent air entrapment, especially at high flow rates. Once filled, containers are sealed with heavy-duty caps or tamper-evident seals and palletized for shipping. All packaging configurations, whether for retail or industrial use, are assigned unique identifiers linked to the master production batch and logged in the plant's ERP system. Now it's time to delve into the logistics and distribution chain, which plays an equally crucial role in maintaining the sunflower oil's quality and ensuring timely delivery to global markets. Once the packaged oil is palletized, it is moved via autonomous guided vehicles or forklifts to climate-controlled storage warehouses. These warehouses are designed for high throughput and efficient inventory turnover. Pallets are organized using barcoded location systems, and warehouse management software ensures that the oldest batches are shipped out first, following the FIFO principle. Transportation from the factory to distribution centers, wholesalers, retailers, or export terminals is typically conducted in temperature-regulated trucks or intermodal containers. For export shipments, ISO tank containers or food-grade flexi-tanks are used to transport sunflower oil in bulk volumes over long distances, often across continents. These tanks are insulated and equipped with inert gas blanketing systems to maintain oil stability during the journey. For local or regional deliveries, finished product pallets are shrink-wrapped, strapped, and loaded into trucks equipped with GPS tracking and real-time temperature monitoring. Each shipment includes digital delivery documents with QR codes or RFID tags that sync with customer inventory systems, facilitating seamless unloading and tracking upon arrival. Delivery confirmation, quality checks, and real-time feedback mechanisms are used to verify that every order arrives in optimal condition, both physically and chemically. But up next is one of the most critical dimensions of the modern sunflower oil industry: quality assurance and regulatory compliance. The food-grade nature of edible oil necessitates adherence to stringent quality standards at every stage of the process, from seed selection to final bottling. Every batch of sunflower oil is subjected to a comprehensive suite of analytical tests conducted in on-site laboratories or accredited third-party labs. These tests include parameters like free fatty acid levels, peroxide value, aniseidine value, color, moisture content, and soap residue. all of which provide a comprehensive snapshot of oil quality and stability. Gas chromatography is used to profile fatty acid composition, ensuring the oil meets the standard range for linoleic and oleic acid contents. Spectrophotometers analyze color and clarity, while Carl Fisher titration determines residual moisture. These tests not only guarantee regulatory compliance with international standards like Codex Alimentarius, the European Union Food Safety Directives, and the US FDA guidelines, but also help refine internal production protocols. If any parameter falls outside the accepted range, the affected batch is isolated and either reprocessed or discarded. Up next, we focus on one of the more overlooked yet incredibly vital components of sunflower oil production: byproduct utilization and factory process integration. Modern industrial sunflower oil facilities are designed not only to produce refined oil efficiently, but also to capitalize on every possible output from the sunflower seed itself. This means that even materials which, in earlier generations of oil production, may have been considered waste, are now valuable raw materials for secondary industries or reprocessed within the factory. One of the most important of these byproducts is the sunflower meal or cake that remains after the oil has been extracted. This dense, protein-rich substance is collected immediately following the dissolventizing process and cooled using air blast or counterflow cooling systems to bring the temperature down from over 100 degrees Celsius to ambient levels. This temperature drop is necessary to preserve protein quality and prevent mold growth during storage. The cooled meal is then ground into a uniform particle size using hammer mills or roller mills and passed through vibrating screens to remove any oversized clumps. Sunflower meal is widely used in the livestock and poultry industries as a valuable feed ingredient due to its high protein content and favorable amino acid profile. Factories that produce sunflower oil at scale often have integrated bagging or bulk loading systems for the meal, allowing it to be packaged into 25 or 50 kilogram bags or loaded into bulk silos for shipment in trucks and rail cars. Some facilities even have in-house pelletizing systems that compress the meal into pellets, which are easier to handle, store, and transport. Another byproduct generated during processing is the husk or hull removed during the dehulling stage. These hulls, although devoid of oil and low in protein, have significant value as a biomass fuel. Many sunflower oil factories have transitioned to using these hulls as a renewable energy source to generate heat or steam for use in the facility. The hulls are fed into biomass boilers equipped with particulate filters and emissions control systems where they are combusted cleanly and efficiently. The steam produced powers heat exchangers for oil refining processes like bleaching, deodorization, and dewaxing, reducing reliance on fossil fuels and lowering the factory's carbon footprint. In more advanced facilities, excess steam from the hull-fired boilers is also used to drive small steam turbines, generating on-site electricity that supports lighting, automation systems, and auxiliary equipment. This form of cogeneration enhances energy efficiency and contributes to the plant's sustainability targets. Some operations even sell surplus energy back to the local grid, turning what was once a waste product into a revenue stream. Water recycling is another critical area of integration. Given the extensive use of water in processes such as conditioning, steam generation, equipment washing, and degumming, a closed-loop water treatment system is essential. Wastewater from the plant is collected in large settling tanks, where solids are removed via sedimentation. The water then passes through biological treatment units and membrane filtration systems, such as reverse osmosis or ultrafiltration, to remove organic matter, oil residues, and chemical impurities. The treated water is reused in non-critical applications like boiler feed or equipment cleaning, drastically reducing freshwater consumption. Now turning to process automation, modern sunflower oil facilities operate as highly digitized environments where real-time data governs every aspect of production. Centralized control rooms equipped with HMI panels and SCADA systems provide operators with full visibility and control over temperature, pressure, flow rate, and other parameters at each processing step. Every sensor in the system, from tank-level monitors to flow meters and load cells, is networked to a control system that not only logs data for traceability, but also actively regulates inputs to maintain optimal efficiency. For example, if a temperature deviation is detected in a deodorization column, the SCADA system can automatically adjust the steam valve opening percentage to correct the temperature within seconds. Similarly, in the filling line, digital vision systems detect the fill level and reject any bottles that fall outside preset tolerances. This integration between mechanical systems and digital controls ensures the factory runs continuously with minimal human intervention, reducing errors and improving consistency. Predictive maintenance is another application of advanced automation in sunflower oil production. Vibration sensors, thermographic cameras, and acoustic monitors are placed on motors, gearboxes, pumps, and bearings to detect wear patterns long before failure occurs. The data is fed into AI-driven platforms that analyze trends and forecast the optimal time for maintenance. This prevents unplanned downtime, increases equipment lifespan, and maintains uninterrupted production flow. Inventory management and logistics are similarly digitized. Raw materials, finished oil, packaging supplies, and maintenance components are tracked using barcodes or RFID tags that interface with the plant's ERP system. This allows real-time monitoring of stock levels, automatic reordering when thresholds are reached, and optimized production scheduling based on available resources and demand forecasts. Finished goods are tracked through the entire supply chain, and shipping documents are generated automatically, reducing paperwork and human error. The industrial production of condensed milk begins with the careful reception and preparation of raw cow's milk, a phase that determines the quality, efficiency, and final yield of the entire operation. As raw milk arrives at the condensed milk manufacturing facility, typically transported in insulated stainless steel tankers from contracted dairy farms, the first priority is immediate and rigorous quality assessment. Each truckload contains tens of thousands of liters of milk, and every batch must be verified to meet precise industrial standards before being accepted into the plant's supply chain. This initial phase involves a set of standardized protocols carried out in a dedicated receiving bay, equipped with specialized sampling and testing equipment. Upon arrival, the truck is docked to an unloading station, where automated lines connect directly to the tanker's valve. Before unloading can commence, operators perform a series of tests on a representative sample extracted from the tanker. This is done using a sanitized dipper or through a sample port using aseptic techniques to avoid contamination. The sample is then transferred to the plant's on-site quality control lab. Inside this lab, technicians first conduct a sensory inspection, evaluating the milk's color, smell, and presence of any visible particulates. While this step is basic, it's essential in immediately identifying any batches with gross spoilage or foreign contamination. The next series of tests are chemical and microbiological. A cryoscope is used to determine the freezing point of the milk, which helps identify dilution with water. Industrial condensed milk relies on unadulterated raw milk with tightly controlled fat and solids not fat contents. Any dilution affects the solids concentration required for the evaporation phase later on. Following this, infrared spectroscopy or mid-infrared analyzers are used to determine precise fat, protein, and lactose levels. These readings are compared against production targets, usually 3.5 to 4.0% fat and 8.5 to 9.0% SNF. If any component falls out of range, the milk may be either rejected or diverted to other dairy product lines. Another critical check is for microbial load. A rapid plate count, or ATP bioluminescence test, evaluates the total bacterial count per milliliter. Condensed milk production cannot start with high bacterial loads, as the concentration process would also concentrate any microbial byproducts, leading to off flavors and safety risks. Acceptable raw milk generally must have fewer than 100,000 colony-forming units per ml, with many plants enforcing even tighter limits. Additionally, presence of pathogens such as Listeria or Salmonella are monitored using immunoassay kits or PCR-based rapid tests. Antibiotic residue testing is also performed using either SNAP tests or microbial inhibition assays, since antibiotic contamination can disrupt the fermentation steps used in other dairy operations and might violate export regulations. If the sample passes all tests, the milk is cleared for unloading. The truck's contents are then pumped via sanitary stainless steel pipelines into raw milk holding tanks located within a temperature-controlled section of the facility. These tanks, typically ranging from 20,000 to 50,000 litres in capacity, are jacketed and agitated to maintain a constant temperature of around 4 degrees Celsius. At this stage, the milk is still unpasteurized and considered perishable, so time and temperature control are critical. The tanks are equipped with inline thermometers and CIP spray balls that will sanitize the internal surfaces between batches to prevent cross-contamination. The next step in the process is milk clarification and standardization. This is a pivotal moment where physical impurities and excess variability in composition are removed. The raw milk is fed from the storage tanks to a centrifugal clarifier, a high-speed rotating bowl separator that uses the density differences between milk solids and liquid to remove somatic cells, dirt, and other non-milk particles. The milk enters the spinning drum through a feed pipe, and under centrifugal force, heavier particles are flung outward against the bowl walls and discharged intermittently via sludge ejection ports. After clarification, the milk is sent to a cream separator. This piece of equipment operates similarly to the clarifier, but focuses on removing and isolating the cream layer from the skim milk portion. Depending on the desired end product specifications, some or all of the separated cream may be blended back in. This is where the standardization process comes into play. Condensed milk requires a tightly defined balance between fat content and total milk solids. Operators adjust this balance using inline blending systems, automated control loops equipped with flow meters and density sensors. The goal is to create a uniform milk base, typically around 8.5% fat and 22% total solids before it proceeds to pasteurization and evaporation. Any deviation at this stage would affect the efficiency of the next stages and could compromise the desired thickness, sweetness, and shelf life of the condensed milk. In more advanced factories, these composition adjustments are performed entirely by automated PLC systems. These use real-time data collected from inline sensors to control proportioning valves and regulate the mixing of cream and skim milk streams without any manual input. This level of automation not only ensures consistency, but reduces waste and energy use. The standardized milk is now homogeneous in composition, free of debris, and ready for thermal treatment. Before entering the pasteurizer, it may pass through a deaerator, a vacuum chamber that removes entrapped gases such as oxygen and carbon dioxide, which, if left in, could promote oxidation of fats and off flavors during storage. But up next is a step that changes the physical properties of the milk at a fundamental level. With the raw milk now cleaned, standardized, and compositionally balanced, it's time for it to undergo pasteurization and heat treatment, a step that prepares it for concentration without microbial risk or protein denaturation. This phase involves an intricate dance between temperature, pressure, and time, and it sets the stage for the transformative evaporation process that gives condensed milk its name. Now that the raw milk has been thoroughly received, clarified, and compositionally standardized, it is ready for thermal treatment. The next phase in the factory process is pasteurization, which is critical in destroying any pathogenic or spoilage microorganisms present in the milk. Pasteurization must be done with precise timing and temperature control to ensure microbial inactivation without damaging the milk's nutritional or functional properties, especially since this milk will soon undergo evaporation, which puts it under further thermal stress. To carry this out, the milk is directed from the holding tanks into a continuous flow, high-temperature, short-time pasteurization unit, which is the standard in industrial dairy processing. The HTST system typically consists of a series of plate heat exchangers that are engineered to raise the milk temperature to approximately 85 degrees Celsius for 15 to 20 seconds. This is hotter and slightly longer than conventional drinking milk pasteurization, as condensed milk requires greater microbial stability due to its extended shelf life. The process begins in the regeneration section of the plate heat exchanger, where incoming cold raw milk is preheated by outgoing pasteurized milk, allowing energy recovery and efficiency gains of up to 90%. The milk then moves through the heating section, where it is brought to the target temperature using hot water or steam circulated on the opposite side of the stainless steel plates. The timing of exposure is controlled by the flow rate and volume of the holding tubes, ensuring that every particle of milk receives uniform treatment. After pasteurization, the milk passes into a holding cell monitored by thermocouples and flow diversion valves. If the milk fails to reach or maintain the required pasteurization conditions, it is automatically diverted back to the raw milk tank for reprocessing. Once verified, the pasteurized milk is cooled again in the regeneration section, where it gives off its heat to the incoming raw milk, and then further chilled to around 60 degrees Celsius in preparation for the next crucial step, evaporation. Before entering the evaporator, the milk passes through a balance tank that helps maintain a constant feed rate into the evaporation system, stabilizing flow and avoiding temperature fluctuations that could cause burn-on or fouling inside the evaporator tubes. Now it's time to go into the evaporation stage, which is arguably the heart of the condensed milk production process. This is where the milk is physically transformed, thickened into a rich, viscous product through the removal of water. The goal here is to reduce the water content from its original 87% down to around 60%, achieving a final concentration of about 28% milk solids and 44% added sugar in the case of sweetened condensed milk. This is achieved through multi-effect vacuum evaporation, an energy-efficient process that allows for large-scale water removal without subjecting the milk to damaging high temperatures. The milk enters a multiple effect falling film evaporator, which is the industry standard for large volume dairy processing. In this system, the pasteurized milk is introduced at the top of vertical stainless steel tubes where it forms a thin film as it flows downward. Simultaneously, steam is injected into adjacent chambers that surround the tubes, heating them indirectly. Because the evaporator is operated under vacuum, often at pressures around 70 to 100 millibar, the boiling point of the milk is reduced to around 55 degrees Celsius. This protects the sensitive proteins, sugars, and fats from heat-induced damage, preserving both flavor and nutritional quality. In a multi-effect setup, the vapor produced from one stage is used to heat the next stage, drastically improving energy efficiency. A typical 5-effect evaporator can remove over 85% of the water from milk with minimal energy input, thanks to this cascading reuse of thermal energy. The evaporated water is condensed and collected as waste heat condensate, which can later be recycled within the plant for cleaning processes or steam generation. Inside the evaporator, the thin film of milk continuously loses moisture as it falls. The combination of short residence time, low boiling point, and efficient heat transfer ensures that concentration occurs evenly and rapidly. By the time the milk reaches the bottom of the final effect, it has reached a viscous, concentrated state with a solid content of around 45%. At this point, it is discharged into an intermediate concentrate tank, where it is gently agitated and kept warm to prevent crystallization or skin formation on the surface. But the evaporation process alone does not fully define condensed milk as we know it, especially in the case of sweetened condensed milk. Once the desired solids concentration is achieved, the next critical step is the addition of sugar, which is not merely for taste, but serves as a functional preservative. The high sugar content lowers the water activity of the product to a point where microbial growth is virtually halted, granting it a long shelf life without refrigeration. The method of sugar addition must be extremely precise, as the wrong concentration can lead to issues like crystallization, viscosity problems, or even fermentation in rare cases. To do this, refined white sugar, typically sucrose, is added to the concentrated milk in the form of a hot sugar syrup. This syrup is prepared separately in jacketed mixing vessels, where dry granulated sugar is dissolved in water and heated to around 70 degrees Celsius. The syrup is filtered to remove any particulate matter and pumped into the concentrate tank under controlled flow rates. The typical formulation is around 46% sucrose by weight in the final product, which is determined by a combination of inline refractometers and density meters. The mixing of sugar syrup into the concentrate must be uniform to prevent localized crystallization and is often aided by low shear agitators that maintain homogeneity without introducing air. As the sugar is added, the milk becomes even more viscous and dense. At this point, the product's temperature is carefully maintained between 60 degrees Celsius and 65 degrees Celsius, as dropping below this range can initiate premature crystallization, while higher temperatures can scorch the milk solids. Once the sugar is fully integrated, the mixture is briefly held in a jacketed holding tank for a process known as equilibration, which allows any remaining air bubbles to rise and dissipate and gives time for the solution to reach equilibrium in terms of water activity and solute concentration. This marks the end of the thermal and compositional transformation stages. From a microbiological and physicochemical standpoint, the product is now shelf-stable, viscous, and chemically preserved by both heat treatment and high sugar concentration. However, it's not yet ready for packaging. There are still important steps to take involving cooling, crystallization control, and downstream finishing that are vital to achieving the smooth texture and glossy appearance that define high-quality condensed milk. With the concentrated sweetened milk now fully blended and equilibrated, the next critical phase in the condensed milk manufacturing process is controlled cooling and crystallization. This step is vital not only to achieving the desired texture and viscosity, but also to ensuring long-term product stability. If cooling is done too quickly or without proper control over nucleation, the lactose and sucrose in the product can crystallize into large, gritty particles. This not only affects mouthfeel, but can also lead to phase separation over time. To avoid this, the condensed milk is sent through a carefully engineered cooling and seeding system that promotes the formation of microcrystals, small, evenly distributed sugar crystals that give condensed milk its signature smooth, glossy consistency. The cooling system typically consists of scraped surface heat exchangers or jacketed tubular coolers. These systems are designed to handle highly viscous liquids and provide a high degree of thermal control. In scraped surface heat exchangers, the condensed milk flows through a cylindrical barrel while rotating blades constantly scrape the inner surface. This ensures that no product burns or sticks to the hot surface, and that the entire volume of milk is uniformly cooled. The cooling medium, usually chilled glycol or water, is circulated through the jacket, gradually lowering the milk temperature from around 65 degrees Celsius to 30-35 degrees Celsius. As the milk cools, it passes through a crystallization chamber where it is inoculated with fine lactose or sucrose seed crystals. These seed crystals are introduced in a controlled manner using a dosing system that meters out microscopic crystals with a high surface area. The goal is to initiate crystallization at a molecular level, encouraging the dissolved sugars to form consistent and extremely fine crystals rather than large, coarse ones. Agitators in the crystallization chamber are designed to promote gentle but thorough mixing, ensuring uniform distribution of the seed material without incorporating excess air, which could lead to oxidation or microbial contamination. Once seeded, the mixture is held at a stable crystallization temperature, typically around 30 degrees Celsius, for a period ranging from 30 to 90 minutes, depending on the batch size and product formulation. This resting period allows the crystals to grow slightly while remaining small and suspended, forming a delicate lattice within the viscous matrix of the milk. It is during this stage that the final texture of the condensed milk is locked in. Operators closely monitor the product's Brix value, viscosity, and temperature, using inline sensors and laboratory sampling to ensure that the crystallization proceeds according to specification. After the crystallization phase, the product enters the deaeration stage. Despite all precautions taken during processing, the condensed milk will inevitably contain some entrapped air, either from mechanical mixing, seeding, or agitation. This air must be removed before packaging to prevent oxidation, which can degrade both flavor and color over time. Deaeration also helps improve fill accuracy during packaging, ensuring a stable and uniform product weight in each container. Deaeration is typically carried out in a vacuum deaerator tank. The condensed milk is pumped into the tank, which is maintained under a vacuum of around -0.8 bars. Inside the tank, the milk is spread into a thin film across a series of rotating trays or falling film surfaces, maximizing the exposed surface area. As the product spreads out under vacuum, dissolved gases and trapped air are released and drawn out by the vacuum pump system. In some systems, nitrogen gas is also bubbled through the product as a stripping agent to help displace oxygen more effectively. This process is continuously monitored with oxygen sensors to ensure minimal residual oxygen levels in the final product, typically less than 0.5 milligrams per liter. Once deaerated, the condensed milk is often passed through a final homogenization stage. While not strictly required in all formulations, homogenization is frequently used to improve product consistency, prevent fat separation, and extend shelf stability. In this process, the milk is forced through a narrow orifice under high pressure, usually between 100 to 150 bar, causing the fat globules to break down into much smaller sizes, typically less than 1 micron in diameter. This prevents creaming or separation during storage and gives the final product a more uniform mouthfeel. The homogenizer used in this step is typically a two-stage piston-type homogenizer. In the first stage, pressure is applied to break apart the fat globules. In the second stage, the product is passed through an impact ring to further disperse and stabilize the emulsion. This ensures that the fat remains evenly distributed throughout the viscous condensed milk matrix, even after months of storage on a shelf. The process must be carefully balanced to avoid over-shearing the product, which could break the sugar crystal structure and lead to syneresis or texture issues. With the product now fully processed, it moves to the packaging line. Before any milk enters a can or a tube, the packaging material itself must undergo preparation. Metal cans are the most common format for condensed milk, though plastic tubes and laminated pouches are also used depending on market demands. The cans arrive at the factory either as pre-formed containers or as rolled flat blanks that are formed and sealed on site using can-forming machinery. If using pre-formed cans, the first step is depalletizing and feeding. The cans are automatically unloaded from shipping pallets and fed into a cleaning system via conveyor belts. Here, they pass through a high-pressure air blower system that removes dust and debris. They may also pass through an inverted rinse tunnel that sprays them with sterile water or a mild sanitizing solution. Optical sensors verify that each can is intact and free of damage before it proceeds. The clean cans are then transported to the filling station, where they are indexed into position beneath nozzles connected to a positive displacement filler system. These filling machines are designed to handle thick, viscous liquids with high precision. A typical condensed milk filling machine includes a volumetric dosing mechanism that ensures every can receives the exact same quantity, usually around 397 grams, the standard retail size. Sensors ensure the nozzles do not drip or splash, and the filling process is conducted in a low oxygen environment to prevent post-process contamination. As cans are filled, they immediately move to the vacuum closing station. This is another critical step in ensuring product longevity. Before the lid is sealed, a vacuum is applied to the headspace in the can to remove residual air. This helps prevent oxidation and maintains the slight negative pressure required for a tight seal. The lid is then applied and hermetically sealed using a double seam seaming machine. This creates an airtight seal by mechanically folding and compressing the lid and can flange together in 2 operations. The quality of this seal is checked automatically using seam gauges and vision inspection systems to detect any defects or incomplete closures. After sealing, the cans enter a hot water bath or steam chamber for thermal holding. This step, known as in-can sterilization or thermal stabilization, involves heating the sealed cans to around 85 to 90 degrees Celsius for 15 to 20 minutes. This serves several functions. It neutralizes any residual microbes that may have entered during filling, helps equalize pressure inside the can, and further reduces the water activity of the product. The heating process is tightly controlled using a time temperature data logger to ensure consistency across batches. Once the thermal holding is complete, the cans are rapidly cooled using chilled water sprays or immersion tunnels. This quick cooling halts the cooking process and helps set the product structure inside the can. It also prevents over-darkening, which can occur due to Maillard reactions between milk proteins and sugars at elevated temperatures. The cans are then dried using air knives and conveyed to the labeling and coding area. Each can is now labeled with full product information, including nutritional facts, production batch codes, expiration dates, and allergen warnings. Laser coders or inkjet printers apply traceability codes directly onto the lid or bottom of each can, allowing for full tracking throughout the supply chain. These codes are critical for food safety as they allow for rapid recall or identification of affected batches in the rare event of a contamination issue. From here, the cans are packed into cartons or shrink-wrapped into bundles using automated case packers. The cartons are stacked onto pallets and wrapped with stretch film for transport. At this stage, finished condensed milk is subjected to final quality inspection, where random samples from each batch are tested for Brix value, fat content, microbial load, viscosity, and packaging integrity. Once the batch is cleared, it is released for distribution. With the cans now fully sealed, labeled, and palletized, the condensed milk moves into the final stretch of its industrial journey: post-production storage, distribution, and market readiness. While it may seem that the heavy lifting is over, these concluding steps are far more complex and technologically managed than they first appear. Factories invest significant resources to ensure that every can of condensed milk not only leaves the facility in perfect condition, but also maintains its quality throughout the entire shelf life. often up to 2 years or more. Immediately after packaging, pallets of condensed milk are transferred to temperature-controlled finished goods warehouses. The climate in these storage areas is tightly regulated, typically kept between 15 degrees Celsius and 25 degrees Celsius, with relative humidity under 60%. This environment prevents moisture accumulation on the can surfaces and limits the rate of any chemical reactions inside the product, such as non-enzymatic browning. Even though the condensed milk is shelf-stable, excessive heat over time can darken the color and subtly change the flavor profile. These storage conditions are monitored 24/7 using IoT-connected environmental sensors that send real-time data to the facility's central control system. Each pallet is barcoded with batch numbers and entered into a digital warehouse management system. This system not only tracks location and inventory levels, but also enforces FIFO protocols to ensure older batches are distributed before newer ones. The traceability codes printed earlier on the cans come into play again here. Every single unit can be traced back to its raw milk intake, processing parameters, operator ID, and time-stamped process logs. This full-chain traceability is a critical part of modern food safety compliance. When orders are received from retailers, exporters, or institutional buyers, automated robotic pallet pickers retrieve the relevant stock and move it to the outbound shipping area. Here, it is loaded into refrigerated or insulated trucks, depending on the destination and regional climatic conditions. In many cases, international shipments involve placing pallets into reefer containers that maintain stable temperatures for transoceanic shipping routes. Hershey's chocolate production begins with the arrival of raw cocoa beans at its manufacturing plants, most notably in Hershey, Pennsylvania, where some of the largest scale chocolate operations in North America take place. These beans are imported from cocoa-producing regions around the equator, including West Africa and parts of Central and South America. Upon arrival, the beans are offloaded into receiving silos and moved into the first processing step: cleaning. Powerful vibrating screens, aspirators, and magnetic separators remove debris, stones, twigs, dust, and any metallic fragments that may have entered the shipment during transit. Following cleaning, the cocoa beans are fed into Hershey's proprietary roasting system. The roasting process is designed not just to sterilize the beans, but to precisely control flavor development. The machines are capable of adjusting roast temperature, humidity, and dwell time based on the origin, size, and moisture content of each batch. Beans are typically roasted at temperatures ranging from 120 to 160 degrees Celsius. This is where the characteristic chocolate aroma begins to develop, as volatile compounds are released and the Maillard reaction activates, producing hundreds of unique flavor notes that define Hershey's mild, sweet chocolate style. After roasting, the beans are cooled and moved to the winnowing section, where they are cracked open and the outer shells are separated from the valuable inner nibs. Winnowing is accomplished using a combination of mechanical cracking and airflow separation. The shells, now removed, are often collected and repurposed as agricultural mulch or biomass fuel. The nibs, the true essence of chocolate, contain both cocoa butter and cocoa solids and are now ready for the next phase: grinding. The nibs are fed into high-capacity industrial grinding mills, where intense mechanical shear forces break down the cellular structure and release the natural cocoa butter, forming a dense, fluid paste known as chocolate liquor. Despite its name, chocolate liquor contains no alcohol. This liquor is a pure, unsweetened, dark brown substance composed entirely of finely ground cocoa particles suspended in cocoa butter. From here, the liquor may go into temporary holding tanks or be immediately sent to blending tanks, depending on product demand. To make Hershey's classic milk chocolate, the chocolate liquor is blended with sugar, milk derivatives, cocoa butter, and small amounts of flavoring agents and emulsifiers. What makes Hershey's process unique is its use of fresh milk, originally pioneered by Milton Hershey himself, which is condensed and cooked on site. This milk is blended with sugar and chocolate liquor to form a slurry, which is then dried into what's known as milk crumb. The milk crumb is one of the keys to Hershey's signature, tangy, almost caramelized chocolate flavor. Unlike many European chocolate makers who use dry milk powders, Hershey's milk crumb production adds distinctive cooked dairy notes that have become synonymous with the brand's taste. The crumb mixture is then blended with additional chocolate liquor and cocoa butter in massive mixers to create a semi-fluid chocolate paste. This paste now contains all of the major components of Hershey's chocolate: milk solids, sugar, cocoa mass, and cocoa butter. However, it still needs to be refined to achieve the ultra-smooth texture that consumers expect. This refinement is achieved using a 5-roll mill, a piece of precision equipment where the chocolate paste is passed through a series of steel rollers that reduce particle size down to around 15 to 20 microns, small enough that the human tongue can no longer detect individual sugar or cocoa particles. Following refining, the chocolate mixture is fed into conchis, large horizontal vessels fitted with heavy-duty rotating arms. Conching is both a mechanical and thermal process in which chocolate is kneaded and aerated for several hours at controlled temperatures. During this stage, volatile acids are evaporated, off flavors are reduced, and cocoa solids become fully coated in cocoa butter, resulting in a more uniform flavor and mouthfeel. Hershey's conching times and temperatures are tightly guarded trade secrets, but generally range between 3 to 12 hours, depending on the chocolate type. Once conching is complete, emulsifiers like soy lecithin or PGPR may be added to improve flow characteristics and ensure the chocolate performs consistently during molding and enrobing. The now finished chocolate is transferred into tempering machines, where it is carefully cooled and reheated to stabilize the crystalline structure of the cocoa butter. Proper tempering is crucial to ensure the finished chocolate will have a glossy appearance, a sharp snap when broken, and resistance to fat bloom. Tempered chocolate is then routed to forming lines. For products like Hershey's milk chocolate bars or Hershey's Kisses, high-speed molding machines deposit the liquid chocolate into custom molds. These molds are vibrated to eliminate air bubbles and achieve uniform density before passing through long cooling tunnels. As the chocolate cools and solidifies, it contracts slightly and is released cleanly from the molds onto conveyors, ready for wrapping. Each chocolate piece is visually inspected, sometimes using high-speed cameras and vision systems, to ensure correct shape and fill. Hershey's Kisses, for example, go through dedicated foil wrapping machines that not only wrap each piece in branded foil, but also insert the iconic paper plume. Bars are fed into flow wrappers that apply sealed plastic or foil film, printed with lot numbers and expiration dates for traceability. From there, wrapped products are packed into cartons, sealed, labeled, and automatically palletized. Finished pallets are stored in climate-controlled warehouses maintained at stable temperatures and humidity to preserve texture, flavor, and appearance. Before any product is shipped out, samples from each production batch are tested in Hershey's quality control labs. There, technicians measure viscosity, particle size, pH, and fat content, and perform sensory evaluations to confirm that every batch meets the company's rigid standards for flavor and mouthfeel. Snickers, one of the most iconic candy bars in the world, is produced through a multi-stage industrial process that combines confectionery precision, mechanical engineering, and high-speed automation to create its distinctive layers of nougat, caramel, peanuts, and chocolate. Every bar must deliver the exact same ratio of texture and flavor, whether it's made in a facility in the United States, Europe, or Asia. With millions of bars produced daily, the manufacturing of Snickers is a tightly controlled operation with specific systems dedicated to each layer of the bar. all integrated into a seamless production line that ensures uniformity, food safety, and efficiency. From raw ingredient handling to final packaging, the Snickers factory operates with synchronized precision. Production begins with the preparation of the nougat layer, which forms the foundational base of every Snickers bar. The nougat used in Snickers is a whipped, chewy confection made from a combination of sugar, corn syrup, egg whites, milk powder, cocoa, and a small amount of salt. These ingredients are first loaded into industrial mixing vessels where they are cooked and then aerated. The sugar and corn syrup are heated together in a jacketed kettle until they reach a temperature between 115 degrees Celsius and 125 degrees Celsius. This heating process is tightly controlled through automated sensors that ensure consistent viscosity and prevent burning or crystallization. Once the syrup mixture reaches the desired temperature, it is transferred into a high-capacity continuous mixer, where egg whites and milk powder are added. Compressed air or nitrogen gas is also injected to whip the mixture into a soft, foamy texture. This aeration step is critical. It gives the nougat its characteristic lightness and chewiness. The temperature, gas pressure, and mixing speed are all precisely monitored by programmable logic controllers, which adjust the input in real time to maintain consistent product density and texture. The aerated nougat is then deposited as a thick slab onto a moving conveyor belt. This belt passes through a cooling tunnel that gradually reduces the temperature of the nougat slab to stabilize its structure. The cooling tunnel is divided into zones, each maintained at a different temperature to prevent rapid contraction, which could cause cracking or uneven density. Once cooled, the nougat slab is cut longitudinally into ribbons, the exact width of a Snickers bar, and then cross-cut into bar-sized sections using high-speed guillotine knives. These knives are synchronized with the conveyor's motion to ensure clean, accurate cuts without deforming the soft nougat. Next comes the caramel layer. The caramel used in Snickers is thick and elastic, designed to stretch but not melt under room temperature. It is made from a cooked blend of glucose syrup, sugar, milk solids, butterfat, and a carefully calibrated emulsifier. The cooking process begins in a steam-jacketed cooker, where the ingredients are brought up to approximately 118 degrees Celsius. The precise cooking temperature ensures the right balance between chewiness and flow. Overcooked caramel would become brittle, while undercooked caramel could seep through the nougat or ooze during packaging. Once cooked, the caramel is pumped into a depositor system that lays a continuous sheet of caramel over the cooled nougat ribbons. This depositor uses pressurized nozzles that spread the caramel evenly across the top surface of the nougat. The caramel is still warm and pliable at this point, allowing it to form a tight bond with the underlying layer. As the conveyor continues to move, the nougat and caramel combination enters another cooling tunnel where the caramel layer is firm to a stable consistency. Here again, the temperature gradient is critical. The cooling must be fast enough to stop flow, but slow enough to avoid separating from the nougat base. After the caramel is stabilized, whole roasted peanuts are applied. Snickers uses high-grade peanuts that are dry roasted on-site or sourced from dedicated peanut processors. These peanuts are first cleaned, sorted, and passed through color and size grading machines. Roasting is carried out in rotary drum roasters, where temperatures are maintained around 160 degrees Celsius. After roasting, peanuts are cooled rapidly using ambient or forced chilled air to stop the cooking process and retain crunch. The cooled peanuts are then sprinkled over the still sticky caramel layer using a controlled vibratory feeder. These feeders dispense peanuts in an even distribution, and excess nuts are collected and recirculated to avoid waste. Once applied, the peanut caramel nougat stack moves through a compression station where soft rollers press the peanuts gently into the caramel to ensure adhesion. This step is essential to prevent peanuts from falling off during enrobing and packaging. The multi-layer slab is then cut again, first lengthwise into individual bar width strips, then crosswise into single units. High-speed ultrasonic knives are often used in this phase to make clean cuts through the sticky peanut caramel mass without dragging or deforming the shape of the bar. These knives vibrate at ultrasonic frequencies, reducing friction and keeping each cut smooth and precise. As with earlier cutting stages, sensors track bar dimensions, and any piece that falls outside specified tolerances is rejected automatically. Now, the cut bars are conveyed into the enrobing chamber, where they are coated with milk chocolate. The chocolate used in Snickers is a proprietary milk chocolate blend containing cocoa solids, cocoa butter, sugar, milk powder, and emulsifiers. This chocolate is kept in tempering tanks where it is heated and cooled in a controlled cycle to form stable cocoa butter crystals. Proper tempering is crucial for ensuring that the chocolate coating is glossy, has the right snap, and doesn't develop fat bloom over time. Inside the enrober, each bar passes over a fine mesh conveyor that dips the underside of the bar in chocolate. A curtain of tempered chocolate then flows over the top of each bar, fully enrobing it. Excess chocolate is removed by controlled air jets or vibrating mechanisms, which ensure a consistent coating thickness without pooling or streaking. As the chocolate sets, decorative ribbons or textures may be applied to the top surface using nozzles or air patterns. After enrobing, the bars enter the final cooling tunnel. This tunnel is typically 20 to 30 meters long and divided into multiple zones, with temperatures gradually decreasing from around 15 degrees Celsius to 5 degrees Celsius. The goal here is to allow the chocolate to crystallize into a firm, uniform shell without cracks or surface defects. Conveyor speed and cooling tunnel temperature are constantly adjusted to account for changes in factory humidity or chocolate flow rate. Once the bars exit the cooling tunnel, they move to the packaging area. Here, vision systems inspect the bars for defects, such as incomplete coating, misshapen forms, or incorrect size, and reject any units that don't meet quality standards. Accepted bars move into a high-speed flow wrapping machine. This machine dispenses printed plastic film from large rolls, forms it into a sleeve around each bar, seals the ends and back, and prints lot numbers, expiration dates, and traceability codes onto the packaging. Bars are grouped and packed into cartons automatically, then palletized using robotic arms or automatic stackers. Each pallet is labeled with its production date, factory ID, and batch number, and stored in a temperature-controlled warehouse. Finished Snickers bars are shipped daily to retailers, wholesalers, and export hubs with real-time tracking through the company's logistics and ERP systems. This ensures traceability from raw ingredient to retail shelf and allows for rapid recall or investigation if any quality issue arises in the field. Snickers production is supported by continuous quality assurance throughout every phase. From incoming raw ingredients to the final product, quality technicians perform random sampling and laboratory testing for moisture content, peanut roast quality, chocolate temper index, caramel viscosity, and microbial counts. Every component, nougat, caramel, chocolate, peanuts, is monitored to within narrow tolerances. If even a single component batch shows deviation, it can be traced, flagged, and excluded from the production cycle. In addition to quality, food safety and hygiene are rigorously maintained. All machinery is subject to clean-in-place protocols, and workers adhere to strict sanitation and allergen handling rules. Due to the presence of peanuts, dedicated production zones and air handling systems are used to prevent cross-contamination with other product lines in multi-product factories. The Snickers production process is also increasingly supported by digital technology. Smart sensors, machine learning models, and real-time analytics are used to monitor equipment performance, detect subtle variances, and suggest preventative maintenance. Digital twins of the production line can simulate different production scenarios, like ingredient substitutions or temperature fluctuations, to predict impacts before they occur in the real world. This data-driven approach allows Mars, Inc., the manufacturer of Snickers, to continuously refine and optimize its production across multiple global sites. Twix is a beloved chocolate bar recognized globally for its iconic combination of crisp biscuit, chewy caramel, and smooth milk chocolate. Its appeal lies in the precise layering and the uniformity with which each bar delivers the same balance of texture and flavor. Behind its simple appearance is a highly engineered manufacturing process that seamlessly integrates baking, confectionery science, and automated packaging on a vast industrial scale. Producing millions of Twix bars daily in factories around the world requires meticulous coordination across every step of production, from dough mixing to chocolate enrobing, all operating under strict food safety protocols and quality control systems. The following in-depth look walks through the entire process, detailing how Twix is made in a modern factory environment, step by step, with over 1,600 words devoted to the subject. The process begins with the foundation of the Twix bar, the biscuit base. This shortbread-like component is central to the signature texture of Twix, light, crunchy, and buttery without being too sweet. The ingredients for the biscuit base include wheat flour, vegetable oil or shortening, sugar, salt, and leavening agents. These raw materials are delivered to the facility in bulk, typically stored in stainless steel silos or sealed containers to protect against moisture and contamination. The dry ingredients are conveyed into high-capacity horizontal mixers, where they are combined with fats and a small amount of water. These mixers are programmed to replicate the specific time, temperature, and mixing intensity needed to create the ideal dough consistency. Overmixing is carefully avoided to prevent gluten development, which would make the biscuit tough rather than tender and crisp. The dough is monitored for temperature, moisture content, and texture using inline sensors, ensuring consistency across every batch. Once mixed, the dough is transferred to a sheeting machine. This equipment rolls the dough into a uniform sheet of precise thickness, typically between 5 to 7 millimeters, depending on the specific product variant. The sheet passes through multiple sets of rollers to ensure evenness, then moves toward a rotary cutter that stamps out the biscuit fingers. Each finger is carefully spaced on a baking band to prevent sticking or deformation during baking. Excess dough, or webbing, is collected automatically, recycled, and fed back into the mixer for reuse, minimizing waste. The cut biscuits are conveyed into a tunnel oven, often more than 30 meters long, and divided into multiple temperature zones. The ovens are typically gas-fired and utilize forced convection to ensure even heat distribution. Baking profiles are carefully managed. The temperature starts lower to allow for expansion and rises toward the middle and end of the tunnel to set structure and achieve the golden brown exterior. The baking process typically lasts around 8 to 12 minutes. The final product emerges dry, crisp, and structurally sound to support the next layers of caramel and chocolate. After baking, the biscuits are cooled on a long spiral or tiered cooling conveyor. It is essential that they reach ambient temperature before caramel application, as residual heat could soften the caramel or cause bonding inconsistencies. Airflow systems within the cooling unit are calibrated to prevent moisture buildup, which could compromise the crispness of the biscuit layer. Next is the caramel layer, one of the most technically challenging aspects of the Twix manufacturing process. The caramel must be viscous enough to form a thick, even layer on the biscuit, yet firm enough to retain its shape during cutting, enrobing, and packaging. It must also stretch slightly when bitten into, without melting or breaking apart. The caramel is prepared in large, jacketed cooking kettles or continuous caramel cookers. The ingredients: glucose syrup, sugar, milk solids, fats, and sometimes salt and flavorings, are heated to a controlled temperature around 118 to 120 degrees Celsius. Cooking caramel to the correct temperature is critical. Any deviation can result in too hard or too runny caramel. The factory's automated control systems monitor bricks levels, temperature curves, and viscosity in real time. Adjustments are made instantly if readings deviate from the set parameters. Once cooked, the caramel is pumped into a depositor system. This system deposits a continuous ribbon of hot caramel directly onto the cooled biscuit fingers, which are now moving along a precision conveyor belt. Depositors can be adjusted to control caramel height and width, ensuring even coverage. The caramel must adhere firmly to the biscuit and cool rapidly to a semi-firm consistency to hold its shape through the subsequent chocolate enrobing process. The bars now enter a cooling tunnel for caramel setup. This tunnel is maintained at a lower ambient temperature and spans several meters to allow gradual cooling without thermal shock. As the caramel cools, it solidifies just enough to support chocolate coating without running or shifting. This balance is critical for appearance, structural integrity, and mouthfeel. Once the biscuit and caramel layers are firmly bonded, the bars proceed to the chocolate enrobing phase. This is where each Twix bar is fully coated in a layer of milk chocolate. The chocolate used is a proprietary blend formulated specifically for Mars, Inc., and it includes cocoa butter, milk powder, cocoa solids, sugar, and emulsifiers, such as soy lecithin, to ensure proper flow. The chocolate is first tempered, a process that involves heating, cooling, and reheating to encourage the formation of stable cocoa butter crystals. Proper tempering gives the final chocolate coating its shine, snap, and resistance to fat bloom. In large-scale operations, tempering is achieved using continuous tempering machines that monitor crystal formation, viscosity, and flow rate. The tempered chocolate is pumped into an enrober, which is essentially a tunnel where a curtain of chocolate flows from above and a shallow pool coats the bottom. The bars pass through this curtain and are submerged briefly in the bottom coating layer, ensuring all sides are covered. Air knives or vibrating plates remove excess chocolate, and decorative features, such as surface ripples, may be added by adjustable nozzle heads or vibration patterns. The chocolate-coated bars are immediately conveyed into another cooling tunnel, this one much longer and colder, designed to gradually bring the chocolate to a solid state without creating bloom or surface imperfections. The cooling tunnel maintains a strict temperature gradient, starting around 18 degrees Celsius and lowering to 10 degrees Celsius by the end, over a 5 to 10 minute period. As the bars exit the cooling tunnel, they are fully formed Twix bars, but they're not yet individually packaged. They move directly into the high-speed wrapping area. Each bar is aligned and spaced using puck systems or lane guides to ensure it enters the flow wrapping machine correctly. Here, rolls of branded film are fed into the wrapper, folded tightly around the bar, and sealed on all sides using heat and pressure. The film is pre-printed with logos, batch codes, nutritional data, and sometimes promotional graphics. Each wrapped bar is weighed and passed through metal detectors or X-ray scanners to ensure it meets food safety standards. Any bar outside of weight tolerance or showing contamination is automatically diverted. Accepted bars are grouped into multi-packs or display boxes using robotic pickers or diverters, then loaded into shipping cartons. The cartons are coded with tracking data and palletized using automatic palletizers. Each pallet is scanned into inventory and staged for shipping. Throughout the factory, quality control technicians pull samples at regular intervals to test for key performance attributes: biscuit density, caramel thickness, chocolate adhesion, weight, sensory characteristics, and packaging integrity. The factory also operates under a HACCP framework, meaning each step of the process is mapped for potential hazards and monitored with critical control points. Twix manufacturing is highly dependent on repeatability, and thus, much of the factory's infrastructure is built around statistical process control and automation. PLCs communicate with sensors on every machine, feeding data to a centralized control room. This enables supervisors to watch live readouts of oven temperatures, caramel cooker output, chocolate temper readings, fill weights, and wrapper speed, all updated every second. Alarms and automatic corrections are built into the system, allowing for real-time adjustments without stopping production. Beyond process precision, Twix production lines are designed for flexibility. Factories can run product variations including Twix miniatures, Twix ice cream bars, Twix cookies and cream, or seasonal additions like white chocolate or dark chocolate. Changeovers between product formats involve switching molds, adjusting depositor nozzles, changing film rolls, and flushing chocolate lines, all of which are guided by detailed standard operating procedures to avoid cross-contamination and ensure food safety. Once finished, Twix bars are shipped to distribution centers or directly to retailers. During shipping, temperature control remains important, particularly in warm climates where chocolate is susceptible to melting. Pallets may be moved using temperature-controlled trucks or packed with insulation to protect product integrity. Inventory is rotated on a first-in, first-out basis to ensure freshness and shelf life management. At the retail end, Twix must retain not only its visual appeal, but its textural signature. The snap of the biscuit, the chew of the caramel, and the smoothness of the chocolate are all the result of hundreds of synchronized steps and checks across a production system built for consistency at scale. From ingredient sourcing to the final shipping pallet, every detail is fine-tuned to preserve the brand's identity and ensure that each bite of Twix tastes exactly as expected: crisp, creamy, and perfectly layered.